The experiments were done up the street, and if you walk across through Building 9 into Building 13, you can find the offices where Bob Laughlin yelled at me and his thesis advisor, John Joannopoulos, for many years. We really feel as though this is a family affair, and we're really delighted that Bob and Dan and Horst all agreed to come and speak today. I want to express thanks on behalf of the physics department to Dave Litzter, the Vice President for Research and Dean for Research, for helping to support this, and for the Francis Bitter Magnet Lab. Bob Griffin also helped support it. And I especially want to mention the David Harris Lecture Fund. David Harris was a student at MIT, and before his death, he discussed with his family a memorial that he would like, and he wanted a memorial which would be a living memorial as opposed to hardware or bricks and mortar. And so his family endowed a fund which provides resources for us to bring distinguished lectures to the physics department each year. And this year, we're especially delighted that that's being used to help support this symposium. So now I'd like to call upon Dave Litzter, who would like to say a few words. Dave?
Thank you, Mark. It says here another welcome. I'm not sure you need another welcome, but I think the reason I was asked to do this is to indicate that this lecture series is an important part of the intellectual life of the Institute as a whole, and that what's happening this afternoon is also important to the rest of the Institute and not just the physics department. So I welcome you. I was thinking about this prize a little bit, and the idea that popped into my head is that very often those of us who do basic science, experimental basic science especially, owe an enormous debt of gratitude to technology, but we seldom acknowledge it publicly. But it's very important, and this Nobel Prize would never have happened without some very important pieces of technology. Sometimes the basic scientists have to develop the technology themselves. And here I see there were three important technological ingredients. The first was these very special materials with very high electron mobility, and those were developed by Horst and Dan together with Art Gossard at Bell Laboratories. Without those, the experiments could not have been done. Secondly, the experiments required very high magnetic fields, and those happen to be available at the Francis Bitter Laboratory and no place else in the country. And so the experiments were done here. I think Peter Wolf will be telling us more later this evening for those who are there about it. And the third bit of technology is something that people refer to as wet technology. Namely, it was the unusual brain of Bob Laughlin, who happens to be able to think about things in a way different from most of us, and therefore was able to explain this. So I think it's going to be an interesting afternoon. In fact, it's going to be a real intellectual treat, and I will sit down so that Bob Griffin can proceed and we can get it started. Thank you.
Well, thank you, Mark and Dave. I'm here because I'm presently the director of the Francis Bitter Magnet Laboratory. And as many of you know, being director of the Magnet Lab has been like being captain of in the last few years at least, being captain of a ship sailing on a really pretty rough sea. some people, one of my colleagues described it as like being captain of the Titanic, even. But we've had some very good experiences, nevertheless, during the last few years, and many of those were associated with visits from Horst, Störmer, and Dan Tsui. I mean, we're very closely connected, of course, with the experimental aspects of the fractional quantum Hall effect. As Dave Lister just mentioned, the fractional quantum Hall effect was actually discovered at the Francis Bitter National Magnet Laboratory at that time, and it was actually approximately 18 years ago today, yesterday rather. I don't know if you realize that, October 7th, 1981, and we're converging to the opinion that the experiment may have been done in cell 4 of the magnet lab. Maybe Horst and Dan can comment on that later on. But we owe Horst and Dan a very great thank you, a very big thank you. They have been an enormous help to the lab, and I think everybody at the lab, particularly myself, really appreciates what they have done for the lab, perhaps more than whatever we did for them. And so I would like to express the gratitude of the laboratory and its members to both of those individuals for all of the nice interactions we've had, and also to add our congratulations to everyone here on the award of the 1998 Nobel Prize.
Thanks, Bob. So now I'm going to call on Ray Ashuri, who was a postdoc with Horst Störmer at Bell Labs before he came to the MIT faculty, to introduce Horst.
Well, it's a pleasure and an honor for me to introduce Horst. Horst has been at Bell Labs since completing his PhD at the University of Stuttgart in 1977. And he started at Bell as a postdoc and a year later became a regular member of technical staff. And following sort of a meteoric rise, 3 or 4 years later became a department head, headed the famous semiconductor physics department, which is where the transistor was invented. And he became, after that, director of physics research in 1991. He's now a professor at Columbia, and he still holds an adjunct director position at Bell. By the mid-1980s, when I was in grad school, Horst was already quite famous. In fact, I remember one of the older students in my lab having boasted, "I saw Horst Störmer." So, and a lot of other adjectives came along with that. But you can imagine then how thrilled I was when he chose me as a postdoc in 1990. So the first thing I noticed, coming into the lab was just an amazing amount of inventiveness and a little bit of outrageousness that I think led Horst to do a lot of great things. The first or second day in the lab, he asked me, "Can you solder?" I said, "Sure, I can solder." I thought it was just soldering wires together. What he meant was, "Can you sit up on this table on top of a stool and solder a couple wires, solder under a microscope on the end of a long probe that we used, a low-temperature probe, and solder little microscopic wires on this sort of flimsy setup." And the idea was, he had an idea for a very novel experiment, and I was a little bit reticent about sitting up on the stool, so he showed me first that it could indeed be done. So it's this kind of spirit that made it just a tremendous amount of fun to be there. Way back when he was a postdoc, he invented a technique for growing ultra-pure semiconductor materials called modulation doping. And this invention was one of the key items, I think, in finally giving rise to the discovery of the fractional quantum Hall effect that he and Dan Tsui did here, as you've all heard. And this kind of structure, actually, it has had some technological relevance in that if you have a cell phone, you've got transistors made out of this kind of ultra-pure material that Horst invented. And some of these ideas that he's had, in retrospect, they seem so simple and maybe even obvious, but of course, before you make the discovery, before you have the idea, it's not at all obvious. And Horst is known, I think, for just seeing with amazing clarity what needs to be done. Here's another sort of outrageous thing that he did. He invented a technique called cleaved-edged overgrowth, which you take a wafer that you grow, it's a very thin wafer, you cleave it inside of a machine that's used for growing these wafers, and you actually grow on this thin edge of the wafer. Okay, this allows you to make, it turns out, sort of perfect one-dimensional structures. And the technique itself is difficult enough, but on top of this, when I came to his lab, he's actually doing lithography on this half-millimeter edge. So imagine doing lithography, the kind that's normally done on big semiconductor wafers, on a very tiny edge. And I was just amazed at the outrageousness of this quest. He actually made it work and has done beautiful 1D experiments on one-dimensional wires since. I also, here I'm blessed with being near Peter Wolf, who was director of the Magnet Lab at the time that Horst and Dan made their discovery. And I just love listening to his stories about Horst and Dan during that time and how they, when they discovered the fractional quantum Hall effect. First of all, they're working inside of a very noisy, big magnet where there's just giant currents running through the spitter magnet, water rushing through it, making the whole system vibrate. This bore is about 2 centimeters wide. Now, imagine you have room temperature outside this bore. Inside the bore, you want it to be 50 millikelvin. So you somehow have to develop a refrigerator that cools your samples down to 50 millikelvin. Horst and Dan did it, and that, of course, is what got them the prize. So you can see how this kind of inventiveness, it's just critical to this kind of discovery. Here's another story about the first day on the job with Horst. He has tremendous energy, and you see this in the way he walks, because you just can't keep up with him. So what I would notice is that he walks so fast that I couldn't walk as fast. So I'd end up running a few steps, then walking a few steps, and running a few steps. And this is how we progressed to lunch every day during my 2 years at Bell Labs. After Horst became director, and that was after my first year at Bell, after a year, he would still come down to the lab, and he would do things like help me change the pump oil. You know, what a completely mundane job for a Nobel Prize-winning director. He's getting up because he's getting sick of this. But you could see in him that there was a real love of just being in the lab. All right. Let me end with this. Horst has received every physics award imaginable, the Buckley Prize, the Nobel Prize, the Franklin Medal, he's in the National Academy of Sciences. He's a truly, I think, extraordinary and rare person, and it's just a thrill to have him here just for the day. Here's Horst.
Is this on? Is this on? Yeah. Ray, you haven't gotten any briefer. But thanks very much. It's just too much honor. Thanks, Ray. I must say, you hear more and more of these things, and you sort of start wondering about yourself. But all I can say, I'm a very lucky guy that has worked with tremendous people, and not just collaborators, but also then in the form of postdocs, and Ray is one of those. And there are several others around, and they give me all this credit, and it's just not true. It's these guys that did it. And that Ray says, help changing pump oil is very easy. It's the only thing I can do. It's a pleasure to be back at what was for many years our part-time home, not far down here, sort of a place you really wouldn't want to call home when you walk into it. It's a loud and noisy environment, but Dan Tsui and I came there for many years doing our experiments, eating cold pizza and drinking warm Coke, looking at data on chart recorder coming out, and singing together with our grad students funny songs from Monty Python. It was a real good time for a few years actually it must be about a decade that we came up here. So it's a pleasure to be back at MIT. This doesn't mean that I haven't been back in the meantime, visiting old friends, and many of them are in the audience. There's actually too many to go through one by one. If I do it, I know I'm going to forget one of them, so I better don't. So we have 3 hours. I'm not sure, the audience, how long you're going to hold out for 3 hours. But I have the advantage of having the first hour, and Bob has the last hour. So let's see what you're going to do. That's my first. Can I take this off? Yeah. No. Almost not. You can imagine we're doing a lot of these recently. Actually, the two of us, Bob and I, have been on a tour through Scandinavia. And we started feeling very much like these gentlemen. And it's just a good one that. And it hasn't stopped much since then. I'm looking very much forward to Wednesday next week. I hope that some of the burden is going to be taken off from us, but I'm afraid it's not going to be condensed matter physics, so it still will be rough going. In fact, when I told Bob that I did this when we went to Stockholm and I had only the pieces with me, I told Bob that I would be doing this, and he said, yeah, and I know who's going to be Pavarotti. So. I told him, of course, the best. So, I mean, actually, along this vein, I thought, there's of course all this. It's a great honor, and it's a wonderful week, and we had a very good time. And how good a time we had is perhaps shown on this one here. You come in the morning, and you're sleepy and not yet shaved and washed because you get off the plane. And so they want you to take a photograph in front of the king. This is the king. Yeah.
I remember, I swear, Lou told a Viagra joke.
No. I tell you why we're laughing, and you know why we're laughing. The Viagra jokes were old by then. So they get you in front of the camera, and what all photographers do is you're never close enough, right? Photographers always do that. And because they have one hand on the camera, they do it like this. So they wanted us to stand closer together, and you know Bob, and I say, I can't. He's, after all, in the middle there, and it's not so easy to get. So Bob started out complaining and said, what do you want? And I started out laughing. So the two of us just blurted out, and you see, this is Luis Ignaro, one of the physiology prize winners, and he looks around, he's just totally flabbergasted how badly physicists can behave in front of the king. So. Well, of course, I mean, it was that one that ended up in the newspaper the next day. My fellow countrymen have had good fun with me because, in fact, there was always this, it raises sort of the question, is he German or is he not? Can we count him as one of ours or not? And this question actually goes on, and particularly because my umlaut, I have an umlaut in my name, and I dropped it when I came to this country because a good friend of mine, Michael Schluter, who is no more, but he told me, drop your umlaut, because A, their typewriters doesn't have it, they don't know what to do with it, and then the smart guys either put an E afterwards, so half of them drop the umlaut, the other half puts an E after your O, then you appear twice in the alphabet, and it's not next to each other. So I dropped my umlaut, but now, of course, they have found the umlaut again, and you wouldn't believe in the last APS meeting, I was in twice. Once with and once without umlaut. But this is what actually somebody from Lucent sent me the next day in the mail from Germany. This is sort of the equivalent of the, I don't know, Daily News probably. This was the front page of it. And when I got this in the mail, my first reaction is to fly home and kill my mother. Because that's me. As a 5-year-old, playing Indians and cowboys in Germany then, of course, no concept of the whole thing. But I thought my mother had given me that picture, but indeed they had shot it off the wall because it's hanging, together with my little brother who's here that they cut out. It's hanging on the wall in my parents' living room. In German, this says here, referring to the picture, our Nobel laureate. And then it says under here, already as a boy, he built a toy train with a rocket propulsion, which is true. What it doesn't say there is here, sort of very small letters here, And by the way, it blew up in his hand and ripped off his thumb, which is also true. It was a long time ago. I have no problem with this anymore. But it certainly doesn't show me as a very good experimentalist. So it was a little bit off. Well, enough of the jokes. Let me try to talk a bit about the fraction quantum Hall effect and see how far I get in. And Dan said that however far I get, he takes the second half. So I want to talk about fractional charges and fractional quantum numbers, and want to give you sort of an impression what this whole thing about. The way I judge the audience is actually that most of you actually know everything about it, and I might as well sit down. But after all, you paid my ticket up here, so why don't I deliver? I don't think I have to say much to this audience about condensed matter physics, but I think let me just perhaps pick up at one point along this thought, and that is one of the big problems nowadays in condensed matter physics is electron-electron correlations, meaning that electrons are strongly interacting, of course, because they are charged, and taking into account the correlation, the motion between electrons as it's forced upon them by the other electrons around them is a very difficult problem. Most of through our life, we get away with very crude approximations. Number one, forget it. Just don't take into account. Twiddle a little bit around with the math and with the dispersion relation, and you're done. But in some cases, electron-electron interaction is everything. For example, in superconductivity is everything, mediated by phonons there. And what I want to show you is another case where electron-electron interaction is everything. And it's only electrons this time around, electrons in 2D that really show very strange behavior indeed. In fact, the strange behavior that it shows, and it's just a pool of two-dimensional electrons, nothing else in a magnetic field. You get fractional charges out, which was, of course, a big surprise. They're new electron quantum liquids, fractional quantum numbers. Flux, magnetic flux can be attached to electrons, at least it looks as if it were attached to electrons. New particles are popping up that can sometimes be fermions and bosons, depending on what magnetic field you have. Huge magnetic fields, as big as the ones that you get next door, or got next door, and you still get a good fraction of them next door, can apparently disappear, 10 Tesla, something like this. 1 million times the Earth's magnetic field disappears, and the carriers that you have seem to be moving along as if there were no magnetic field. There's a mass popping up which has nothing to do with the mass of the electron. And they may even superconduct in some sense. Let me see whether I get to this, give you a bit of an impression. We're working on two-dimensional electron systems, and you can create two-dimensional electron systems as three-dimensional worlds, always at an interface between two. Is there something? Yeah, always an interface between two things. So you could do it on the surface of helium, and it is being done on the surface of helium, or on the surface of anything. Typically, things are dirty. This is no comment about your floor. It's just dirty in the sense microscopically that there are dangling bonds where the electrons get stuck. So it turns out actually the best way to make a two-dimensional electron system is at the interface between two things, between two semiconductors, inside a semiconductor. The technique to do this was actually developed, invented in the 70s by Al Cho at Bell Labs, and it's a high vacuum evaporation technique where you basically evaporate two semiconductors on top of each other. So this is a high vacuum chamber, and you evaporate gallium and arsenic, gives you one semiconductor, gallium and aluminum, and arsenic gives you another semiconductor. That's all you need to know. And you grow it on a substrate which provides a template so that the atoms go into the right place. Otherwise, it's just like ball bearings in a sense. Otherwise, it would be random. So you provide a nice underlying lattice for it to grow. And as you know, in order for semiconductors to conduct, you have to throw some dirt into it. You have to dope them. And in this case, actually, silicon becomes the dopant. So silicon is the stuff that gives off an additional electron that then can move around in the material. The way this looks is like this. This is about 2-inch diameter. What is dark here, disregard these things up there. Actually, they have something to do with what Ray brought up, and that is this cleaved edge overgrowth. This is not important. It's just this part down here. This is the wafer. So they're shiny semiconductors, look like a silicon wafer, basically. And the reason that they're black here is because the background was black. But this is a shiny surface of about 2-inch diameter, which then has been grown by MBE. And the important aspect of this is that you have incredibly control in the z direction. You can grow these layers one layer after the other. So what you see here in the cross-section is 4 layers of gallium arsenide, 4 layers of aluminum arsenide, 4 layers of gallium arsenide. This is the black and white stripes. You have a control that's within 1 atomic layer. And this is, so you form these layers that fluctuate by not more than 1 atomic layer, so about an angstrom. Those are the flattest surfaces that you can create with a control of really 1 layer. You know you can stop at 5 or at 6 or at 7 layers. And this technique that was developed and invented in the 1970s, we had then used in order to make very high mobility 2-dimensional electron systems. In 3 dimension, there's sort of a catch-22 when you dope something. You throw in the silicon, which gives off the electron that then moves through the semiconductor, but you're left with the charged impurities, of which the electron then very often bounces off. So yes, you introduce carriers, but you also introduce a scattering for it. In 3D, you hardly can get around it. In 2D, you can, because in 2D, you can put the electrons in 1 layer and the dirt in the other layer, and therefore they hardly see each other. And this is the method to do it. It's called modulation doping, which is, so the green is 1 semiconductor, the blue is the other semiconductor. You put the impurities into the green semiconductor, and they wander over into the blue semiconductor because there they find lower energy. This is a quantum well of about 100 angstrom thickness, and the electrons now can move in this plane, but they cannot move in the z direction because they're tightly confined. In fact, they're so tightly confined that quantum mechanics plays an important role. They're confined that you see the first bound state and the second bound state, and they're separated by about, let's say, 10 millielectron volts. So quantum mechanics is an important aspect of this. If you only have the lowest state occupied and not the second one, the electron in the z direction has no degree of freedom. It's just tight. It cannot do anything. But it can move in the xy plane easily. In fact, very readily, because it's such a nice plane and the impurities are away from it. So you get a very high mobility 2-dimensional electron system in which the electron can run for very long distances before they scatter with anything. The electron density is about 10 to the 11, which makes about an electron every 300 angstrom, something like this. Typically 10 to the 11. You can vary, but that's a typical density that you will find. Mobility is nowadays as high as 10 million. In fact, last week, no, it's the week before, 2 weeks ago, we had a record of 23 million mobility, which is unheard of. I mean, I show you a little bit more about this. You may not understand what mobility means, but it's a mean free pass of about 100 microns. In fact, 20 million is about 200 microns. So the electron travels in this plane for about 200 microns without bouncing into anything. And 200 microns is really big. It's about, well, the thickness of your fingernail, which doesn't look so big, but on a microscopic scale and on a lithographic scale, what we can do nowadays, it is a huge mean free pass. And it's these 2-dimensional electron systems which then we can regard as a 2-dimensional metal. They're basically nothing else but that, with a very long mean free pass. So it means that the lattice behind it hardly plays any role. It's like a 2-dimensional electron system just in free space. Now this technique was invented around 1978, something like this, by these 4 guys. And I show it to you for 2 reasons. The one is sort of a historical picture in terms of MBE machines. This is how MBE machines look then. In fact, what you did is this is very high vacuum. These days, you still opened it up, let all the air in, stuck your sample in, pumped it out overnight, and the next morning you did your growth. You don't do this anymore. Much cleaner than that. The people standing around here is Willy Wigman, Art Gossard, Ray Ingle, and this is me in an earlier incarnation, standing around the MBE machine for the photographer. And the other important part what I'm showing to you is Art Gossard. Art Gossard was a person that grew the sample on which we then discovered the fraction quantum Hall effect. And this was the first time mobilities went as high as 90,000. And that what made it all possible. And it brought it actually about. So the sample is the most important ingredient to all of this. And Art Gossard and his assistant, Billy Wigman, they grew the sample. And it's really unfortunate that they didn't share with us in that prize. They shared with us in some previous prizes, but not in this one. And I say it's unfortunate because I think for us condensed matter physicists, materials is just the most important aspect of our work. The people that have first hand on materials are the ones that very often are ahead in the science that they're doing, because it's really the materials that gets them to this initial step from where you then can start playing. So art and MBE technology is a very important aspect of all of this. So what you end up with then is a two-dimensional electron system where by the separation of electrons from the dopant impurities and then the suppression of scattering from those. Is there any kind of a pointer? Oh, all right. You get very high mobilities. At very low temperatures, you get very long mean free paths. So it looks a bit like a billiard table in 2 dimensions. Electrons can only move in 2 dimensions. Oh, there is one. Yeah, right. I should, yeah. Oh, this is this little guy there. Great. Thanks, Mark. Let me show you how an MBE machine looks nowadays and the people that are running it. This is the crew nowadays that is making this 23 million mobility sample. Actually, the most important guy, Lauren Pfeiffer, and his assistant, Ken West. This is Kirk Baldwin, who's an assistant with me, and this is Amir Yacobi, who was a postdoc at the time. So now the MBE machine is about that big, and you use much cleaner methods in order to get to such high mobilities. But again, these are the important guys to which we owe everything. I'm very often being asked, why at Bell Labs? Why fractional charges? Is it ever going to be in the telephone system? And my only answer to this is only going to make our vacuum cleaners run only 1/3 speed, and that's about all you bet. And it's a joke. Fractional charges will not have, I don't see fractional charges having any kind of application even in the long run. But there's another aspect of all of this work which has an application, and that's this one. Out of exactly the same material, exactly the same material in which we discovered, Dan and I, discovered the fractional quantum Hall effect, out of the same material you can make field effect transistors. It just looks like this is what is in every PC. It's a MOSFET, never mind what it is. This thing just looks the same, but it's another material, and this specific technique of modulation doping creates mobilities that are much higher than here. And contact resistance are low and all of this. So these transistors, or transistors made out of these materials, are the fastest and lowest noise transistors in the world, still today. This is one built by Fujitsu, who actually was one of the first that made a microscopic transistors out of this. Never mind what the structure is. But this is the fastest low noise transistor that you can get. And it's in any of those around the world. Each one has one of those, radio telescopes. This is not a very big market. There's just about probably 100 or 200 around the world, so you cannot make money with that. But you can make quite a lot of money with these things. So a lot of these high-frequency 2 gigahertz telephones that cellular phones have in the front end, which is, well, I don't know, the microphone is front end maybe up there, have one of these HEM transistors for very good performance, and the base stations have it in there. So there is another part of this modulation doping, which is not basic science, but really technology. And I feel very fortunate that on one side, this modulation doping that we invented led to very basic science, and on the other side, it also led to an application. And it's not so that the one came after the other. I think it's an important lesson, and we're not the first to teach this lesson in a sense, but the material is not the first to teach this lesson, that it's not always an invention, fundamental physics, and then there's application. Very often these things go in parallel, and very often actually they go backwards, because the progress in technology is so important for us to do the next step in science too. Okay, let's get a little bit closer to the fraction quantum Hall effect. If you have such a system, particularly if it's semiconductors, the easiest thing you can do, apart from measuring its resistance, is to measure the Hall resistance. All it is like a resistance measurement, but in addition, you put a magnetic field on. So this is a 2-dimensional electron system. You run a current down it, and you put a magnetic field onto it. Then you measure 2 characteristic voltages. The one is along the current path. The other one is across the current path. The one is nothing else but the resistance, and the other one should be 0 as long as there's no magnetic field because the thing is symmetric. But when you put a magnetic field on it, then you push the carriers to one side because of the Lorentz force, so you build up a voltage. Eventually you build up a voltage from one side to the other. That's what you measure. And the voltage that you measure divided by the current, because it's proportional to it, so if you double the current, you get double the voltage. So you normalize it to the current, you get a resistance, a characteristic resistance, which is called the Hall resistance. And as Edwin Hall had already figured out in the last century, I showed this next view graph, Rxy, this resistance is proportional to E, to the magnetic field, and inversely proportional to the carrier density in the material. So it's a wonderful way of measuring carrier densities in material, particularly in semiconductors, because you see the small n, the easier it is to measure. The small n, the bigger this number is. And typically, carrier concentrations are small in semiconductors as compared to metals. So this is a wonderful way of measuring carrier concentration, and it's an industry standard. So this is the first thing you do. And we've done this, of course, but Edwin Hall had done this already in the last century. This is why it's called Hall effect. He was a graduate student, by the way, at Johns Hopkins in 1879 when he discovered that in a very thin foil of gold. He just did this experiment that I showed you, and this is the result here. In fact, there's another aspect to all of this, which I always enjoy, and this is for all of us that are writing papers that have to be 3.5 pages and not any longer. It's interesting to read this introduction here, right? We have to fight with every word, take a word out and make an acronym out of it so that you save another 5 words. This starts out with, sometimes during the last university year, while I was reading Maxwell's Electricity and Magnetism, I mean, by that time you were already over your page limit nowadays. The other aspect is just like it is expensive nowadays to publish color figures. It must have been expensive then those days to publish any kind of a figure, so his results are here only in form of a table. So I had to sit down and, for the first time, plot up Edwin Hall's data. And here's Edwin Hall's data now on a graph. Here it's plotted. This is the Hall, what we could call nowadays the Hall resistance. It's actually a current through the gold leaf divided by the current through a magnetometer versus magnetic field in units of the Earth's magnetism. One does not know what these units are, but one knows that it's proportional to the magnetic field, so that's fine. So this is magnetic field, this is the Hall resistance, and you see those are his data. It's a very nice straight line, just as we know. And of course, since then, this experiment has been done in many ways by many people, and it's a perfectly nice straight line. And the slope of this line here gives you the carrier density of the material. The steeper it is, the less carriers are in there. So this was the status until 1980, when Klaus von Klitzing came along and told us that this is not so at all. In fact, in 2 dimensions, it's not so at all. This is the original result, Klitzing, Pepper, and Dorda in 1980, and it's plotted in a different way than Edwin Hall would have plotted it. So I show you the way similar data, it's not the same data, but similar data looks if we plot it like Edwin Hall plotted it. Magnetic field, Hall resistance. This is the Hall resistance. I talk about the other one in a second. So Edwin Hall would have told us this is a straight line. And Klaus von Klitzing found, of course, this is a very nice example. The steps were much weaker when he saw him. But there are lots of steps in there. This is not at all a straight line. The steps are in there. And not only are the steps very flat and sometimes very wide, but they're also quantized to units of HOE squared, to an accuracy nowadays of a few parts in 10 to the 8. So a few parts in a billion almost, right? A few 10 billions, accurately quantized to this ratio of natural constant. This came as a big surprise. In fact, there are some inklings in the theoretical literature that sort of foresaw this in some sense, but not really pointed it out. You experimentalists should, and it was obscure. But Klaus von Klitzing discovered this actually at the Magnet Lab in Grenoble, the sort of sister institution in Europe. So this is not at all a straight line, but it's plateaus and it's quantized. And I show you also what the resistance does as a function of magnetic field. That's the other property. It looks like the derivative of this. So whenever this is flat, it's actually a deep minimum. And then when it makes a transition, you get a spike out of it. So the magnetoresistance looks like the derivative of the Hall resistance. I show you this because later I sometimes show you this data because they're sort of more dramatic than even the Hall resistance. But it's the same the origin it has the same origin. Here comes my 2 view graphs explanation of the integral quantum Hall effect. If you put a magnetic field on a 2-dimensional electron gas, then the electrons classically perform rotary motion around the magnetic field. So quantum mechanically, this is just a harmonic oscillator. So this is my quantum mechanical oscillator. And then there are bound states in there, and there's only a certain number of bounds. Well, there's an infinite number, actually. But they're discrete, and there's nothing in between. So the electron can be in this state, or in this state. And nothing in between. So in a 3-dimensional electron gas, there is actually something in between, but in 2D, there's nothing in between. And therefore, there's only allowed states at this energy, and at this energy, and nothing in between. I forget the spin. I leave the spin out for most of my talk. It just complicates matters here, but it's very easy to take it into account. The other aspect of it, of this quantization, is that the number of electrons you can fit into a square per one of these Landau levels, as they are called, is only a ratio of natural constant and proportion to the magnetic field. So you take this wave function, you make sort of a size out of it. You take a cookie cutter and just cut out, see how many fit in there, and you see that the number of electrons per level is just E times B over H. And it's independent of the mass, it's independent of epsilon of the material, it's independent of everything. It's just EB, only proportion to the magnetic field. So the integral quantum Hall effect actually happens when I fill up an exact number of these states, of these Landau levels. And you can see that very easily. You take the number of electrons per level, which is EB over H. Then if I, 1, 2, 3, 4 of these levels is filled, then it's just I times D. You put this into the equation that I showed you earlier that Edwin Hall derived already in the last century, and you get the result, H divided by I squared. So it's really trivial. There's a big but here, and this took ingenious people to figure out, because what you assume in there is that the number of electrons in a certain sense is quantized, and that the system is ideal. You do it here. But it's never like this. The number of electrons is fixed once and for all, and you never have an exact number. Never have an exact number of Landau levels occupied, except for singular points. So all this says is that this is my Hall line here, along the magnetic field line, there's a few discrete points where when I go up, this resistance is exactly this number, but it doesn't say that there's any plateaus, so I wouldn't even know where they are. So this is a bit of a fake doing this way, but I cannot go much deeper into it. What it tells you is that this connection between the quantization of the Hall resistance and the two-dimensional system, two-dimensional electron system, has something to do with filling up exact numbers of Landau levels. And this big but here has to do with localization in 2 dimensions. It's actually an important aspect. If you had an ideal 2-dimensional system, you would not see the quantum Hall effect. It requires dirt in order to see it. I think this is sort of totally counterintuitive. You need dirt, you need impurities, you need localization of electrons in there in order to see it. In fact, the guy that figured it out is going to give a talk sometime today. I will not go through this argument, of course, but the bottom line of Bob's argument, one way of at least of looking at it, is that Rxy, this resistance, you can actually regard it, which is this number, you can actually regard it as a ratio of flux of magnetic flux quantum to the electronic charge. So it's a ratio of flux quantum to electronic charge. And therefore, you can look at this, at the quantum Hall effect, if you turn this argument around, as being a measure of E. So that is a very accurate measurement of the electronic charge, which is then the flux quantum divided by whatever you measure. And then this is an integer, and the integer you always know whether it's 1, 2, 3, or 4. You cannot be that far off. So it is one way of looking at the integral quantum Hall effect that is a very accurate measurement of the electronic charge. The other aspect that I always found perplexing is that you measure something to an accuracy of a few parts 10 to the 8 in a sample that looks as terrible as that one. This is about 3 millimeters wide, perhaps 15 millimeter long. This is indium here that is put on and diffused in order to make contact. The black part is actually the surface of the semiconductor, which is really shiny. These parts have been scratched away with an ultrasonic scratcher, really a very intrusive method. And those are gold wires running off here. This is a sample that was made by Dan Tsui. I would have done a much nicer job, but I'm sure that my context wouldn't have worked. Dan's worked, and in fact, that's the sample in which we discovered the fraction quantum Hall effect. So in terms of the integral quantum Hall effect already, it is always so amazing that independent of geometry, independent of how you put your contacts on, you measure something, a quantity, to a few parts 10 to the 8. And of course, this is the essence of a standard, that it does not depend on in this case, on the geometry at all. You can even make a round sample with all contacts on the edges. As long as you do that, you also measure it. This is a picture that's probably going to bring some emotions up in some of the people that are sitting here in the audience. Certainly Larry, I would think. This is, I don't know which cell it is, but Larry can tell us. Which cell is it, Larry? It's downstairs someplace, yeah, I think so. This is 23 Tesla, I suppose. Picture that was shot much later. Dilution refrigerator, that's the fridge. This is the can for around it. This is the pumping system. A person is about as big as this pumping system. And we went with samples to the magnet lab and did experiments with in high magnetic fields, and later on then with a dilution refrigerator. This is about 10 years later, I would think, but still when the Francis Bitter National Magnet Lab was up here. Well, it still is up here, only without the national. It was Dan and I were coming up here for several years to do experiments, and we were typically getting up on Sunday morning, driving up here, having a long 4-hour chat. Depending on who was driving, it was either 3 or 4 hours. 4 or 5, I should say, I think. We're not that fast. And we had this brand new sample from Art Gossard. We're doing experiments down in whatever cell. I don't know which cell it was. We're working on silicon MOSFETs, actually. Dan had invited me to come up with him. He was there already since quite a while doing experiments on silicon. And then with this new sample, we started working together on this modulation dope systems. So here's the result of October 6, 1981. This is the Hall resistance. This is a magnetic field, just what Edwin Hall would have done, and it's a very nice straight line. This is an offset here, so they get it still on the chart recorder paper. It's an old technology to take data. You take a pen and pull it over a piece of paper, and then you look at the trace, and that's what your data is like. There is actually, this is my handwriting here. This says laser upstairs. You see these spikes here? There was I don't know which laser, there was a powerful laser upstairs, and wherever they yanked it, we got a big signal down there. So this is from the laser upstairs. Just had to make sure that this was not physics, but just a dirt effect. But otherwise, it's just a nice straight line, just as Edwin Hall would have said. But there are already deviations coming up here, and these deviations are from the integral quantum Hall effect. We knew exactly where they were, where they had to be. So the top line is basically a repetition of this, taken at 4 degrees. And when we pumped lower, to lower temperatures, indeed, these structures became nice flat Hall plateaus, and that was the last Hall plateau and the second last Hall plateau. Everything, all the world was in order, but it got out of order up here. What you see up here is that at a magnetic field that is about 3 times as high as this one, remember, this is the last Hall plateau. This is the last time the Fermi energy can be between 2 Landau levels. From then on, it's always in the lowest Landau level. So there was nothing expected out here. Actually, I should say, the reason we looked at these things was because Dan Tsui at the time wanted to look at the Wigner lattice, and he had done that already in silicon, and we thought, well, let's look at these materials and see where's the Wigner lattice. The Wigner lattice is when the electron condenses into a regular array of electrons, a hexagonal array or triangular lattice I should say, it's not hexagonal, triangular lattice of electrons that become immobilized and they form a nice 2-dimensional lattice. This was a prediction back then. There are now some indications over the years that something like that indeed exists, and that's what we were looking for. And what we saw is this plateau there. Well, it's not a plateau yet, but it's sort of a inflection point. And we got all excited about it. But of course, it could be all sort of things. I mean, samples resistances very often shot up or they shot down, but this one looked sort of clean up here, but then it developed this thing, which just looks like the integral quantum Hall effect at a higher temperature, but at a different point. And we were standing there, down in whatever, cell 4, and in about 15 seconds, Dan did the following, and I always tell this because I think it's just wonderful and tells you a lot about Dan Tsui. He took this into his finger, the distance from here to here, and he counted off how often he could count it off until he got to this magnetic field. So it was 1, 2, 3. And he said, 1, 2, 3, quarks. Right? And we both had a very good chuckle about it because it was so humorous that, of course, quarks are elementary particles that, with which a charge of 1/3 is associated. And of course, we're not doing elementary particle physics. The highest voltage we have applied in our system is about 10 millielectron volts. So this is a small m. This is not a capital M, and it's certainly not a G. So it was a good joke. But at the same time, he was dead right, because that it had something to do with a charge of 1/3 really turned out to be correct. And that just shows you tremendous insight of Dan. So this is the argument written out. If you take Bob Laughlin's argument at the time, which is that the electronic charge, or whatever you measure, is just the flux quantity divided by this, and you take it seriously, that's what you get out. Just put the numbers in, and this is just this 1, 2, 3. It's 1/3 of an electronic charge somehow involved. If you take it literally. So of course, at the time, it wasn't clear whether it was really a step or not. After all, it was only a slight inflection. It was only an inflection here. So the question was whether it was a step or not. And we had to look closely whether it actually was a step. You see, this says here, this is not a step. I often show this view graph, and I do it nowadays on different continents. This is the only one that can laugh about it. You go to Europe, there's just dead silence. They don't get this joke. And you know why not. This country is run by lawyers. So going to lower temperatures, what was an inflection point really became a pretty nice plateau, and I always say it's a few parts in 10 to the 4, that this was at 1/3, and it was quantized to about 3 times h over e third. So h over 1/3 e squared, I should probably put it. And simultaneously, the resistance, the magnetoresistance, actually developed a deep minimum, which wasn't going yet all the way down, but it looked like it, as a function of temperature, it was going down. Another picture of the time a little bit later, down, that was now around the hybrid magnet, is this one. This was taken on February 16, 1984, about 3 years later, but it's the only one that I got. And those were people that are working with us. This Albert Chang, this is Peter Birkeland, Greg Bobinger, Dan Tsui, and myself here holding up a sign, 85 millikelvin, 280 kilogauss. Peter Birkeland was the guy that developed this, built this dilution refrigerator that's sitting down here. And there's a postdoc and a grad student, actually an MIT grad student, that Peter Wolf told us about. Peter said, I got a good grad student, you want one? And we said, sure. And Greg just became a terrific collaborator. He's nowadays director of the magnet lab at Los Alamos. There's one section that's in Los Alamos, and Greg is running this now. So he's still sticking to magnets like most of us. We fell in love with magnets. Cannot get away from them. Must have something to do with the attractive force. So it very quickly became clear that different from the integral quantum Hall effect, and this, you have seen all this, so I'm not going to go through it. It was the argument that the fraction quantum Hall effect is not a single particle effect. It does not come about from the interaction between from the quantization of individual electrons in the presence of an electric magnetic field in a semiconductor, but it had to do with interaction between electrons. It must come from this because all of the steps that come about from quantization of individual electrons were all expressed in the integer quantum Hall effect already. There shouldn't be anything else. And they were, I think, the smartest and brightest of the theorists were trying to figure it out. for quite a while. And this here's Bob. And he says, nothing yet. How about you, Newton? So with an apple from hell about to drop onto him. And of course, you're going to hear more about it, but this is what he came up with. This is his wave function. And I always express that I find this an immense achievement that the behavior of some 10 to the 11 electrons, you can describe everything with an equation that has just about 15 digits in them, 15 letters in them. This is Bob Laughlin's wave function. He's going to tell us more about it. But this is the solution. This is, within quantum mechanics, everything we can know about it, including all the interactions between the electrons. Bob will modify that, I suppose. But let me tell you about the fraction quantum Hall effect and its origin from a slightly different point of view than that we have developed over when I say we, the theorists have, and I'm just a poor interpretation of the theorists' work. One way of looking at the fraction quantum Hall effect nowadays is from the point of view of the attachment of magnetic flux to the electrons, which is driven by electron-electron interaction. The electrons try to be at the position where there's no other electron. They have to do that for Pauli principle reasons. But the more you get the other electrons away from you, the better it is for Coulomb reason because of the Coulomb interaction with the other electrons. So since the wave function have zeros, many particle wave function has also zeros. They try to attract as many zeros of the wave function onto them. It is advantageous in terms of energy. And one way of describing that is in terms of what's called Chern-Simons flux. It's similar as if you had attached to the electrons a magnetic flux. I won't go any further into this. It takes theorists to do it, and certainly much more time. But then the particle statistics is actually changing. If you take two electrons, you change them around, and they're fermions, the wave function gets a -1 in front. So they're fermions. If you take two electrons with a vortex attached, with a Chern-Simons flux, let's just call it magnetic flux attached to them, you exchange them, you get also this minus sign, but because there's a magnetic field and you move the electrons around the magnetic field that's stuck to the other electron, it gets an additional phase change, and therefore the -1 is multiplied by another -1, so it's a +1. If you stick 2 on it, it becomes a -1 again. If you take 3, it becomes a +1. So these behave like fermions. These behave like bosons, these behave like fermions, these behave like phonons. In fact, whenever M is odd, it looks like a boson, and whenever M is even, it looks like a fermion. And there's a long list of people, I couldn't list everybody on here, there's a long list of people that over time have developed this picture. So there's a way, which I call here another way, because I don't have the time to show you and Bob is going to speak later anyway. So one way of looking at the fraction quantum Hall effect at 1/3 then is to take electrons, imagine there's 3 flux quanta attached to them by virtue of the electron-electron interaction, which forces them to have zeros on the wave function, but just look at this as being magnetic flux attached to them. Then I look at these particles as new particles, which are no longer fermions, but bosons now. And these new particles now are green little spheres rather than red little spheres with 3 arrows on them. So I have now a system of green little balls. And the red balls plus flux quanta have been transformed into these green balls. And they are now bosons rather than electrons. In a magnetic field, actually, they become bosons in no magnetic field because all of the magnetic field has been sucked in by the electrons. They're attached to the electrons. They don't see the magnetic field anymore. This is sort of a jump that I'm making. You have to really think more deeply about it, particularly since I'm saying it's Chern-Simons flux, not real flux. There are deep issues down there. But just for the purpose of this talk, we take the electron with 3 flux quanta attached to them and make out of them what's now called composite bosons in the absence of magnetic field. Then you have a new system of composite bosons where the magnetic flux has disappeared, and this system then is at 0 magnetic field, and bosons condense into a Bose condensate. Superficially, certainly, and indeed that's one of the ways you can look at the 1/3 state, that you do this, take electrons, put flux quanta, make new particles out of them, bosons in 0 magnetic field, and they condense into a Bose condensate, and that's what the 1/3 state is. So you can look at it as a Bose compensation of composite bosons. This is actually historically backwards, but it's pedagogically a little bit easier to do it this way. Now that's the 1/3 state. How about all these other states? And there's a slew of them. The 1/3 state was just the first, and then there are tons of other states that came about. And here I show you what is the magnetoresistance, which looks like the derivative because it's more impressive. And I apologize actually for the picture because it's old by now. In the meantime, there's probably 5, 6 more oscillations here. So there's 1/3, 2/5, 3/7, 4/9, 5/11, 6/13, 7, whatever, up to 21. So you see all these other fractions. The integer quantum Hall effect are these deep minima here. All the rest is fractions. It's not just the 1/3, it's just a slew of things, of fractions. This is a list of fractions that have been seen. We can argue about to what degree we trust each of these fractions, but this is just my way of writing it down. I say this one is okay, and I think actually recently we just have seen something that looks like 6/23. So it's up here. You see a slew of fractions, not just 1/3, was just the first one to be discovered. So what's the origin of this case? It makes it a little bit dizzy that suddenly all of these fractions, a little bit like these chaps here. There's a guy reading the music down here, and you say, gee, look at all these little black dots. It's totally confusing what's happening there. The first thing actually that one was looking into, and is this state at 1/2. See, there's something at 1/2. It doesn't look at all like this other fraction that have this nice minima. The 1/2 state is a broad little thing. It doesn't do much as a function of temperature. This is a low temperature, 100 millikelvin, 25 millikelvin perhaps. It doesn't do much. It just sits there. And the 1/2 state was for a long time a miracle, sort of what this thing is all about. But then one had a description of it, and the people that are most responsible for that are actually these few here, but then also Janandra Jain, who actually, again, is historically backwards. I get to it. So in the same vein of what I told you about electrons flux quanta onto it, you can then look at the 1/2 state where there's only 2 flux quanta per electron. You attach those to it. And as I told you earlier now, they look like fermions again, but they look like fermions without a magnetic field. All the magnetic flux is on the electrons, and therefore you get now pink particles that behave like fermions, but in the absence of a magnetic field. And therefore the magnetic field has been eaten up. The electrons are moving around just like in zero magnetic field, but they're fermions, and not but they're fermions. They remain fermions in spite of the fact that 2 flux quanta have been attached to them, or just because, actually. And we know what a system with, that is fermions in zero magnetic field does. It fills up a Fermi surface. That is exactly actually what was found and was predicted first, but then was found experimentally in various experiments by Bob Laughlin. Sorry, what am I saying? Bob Willett. Bob Laughlin has just become an experimentalist, what he always wanted to be in life. So I made you one. This is just a caricature. It's just a cartoon of it. This is so you find it in K-space. A circle like that, the Fermi edge, and you can measure this. Never mind the factor of 2. In fact, this difference of a factor of 2, actually square root of 2, was an important aspect of that. Yes, this really looks like it. So this was found that the electrons at 1/2 form a new Fermi surface, just like in zero magnetic field. And then so we have only 1/2. So what are all the other fractions? And all the other fractions that one can look at in this way, and that's really historically sort of the starting point of it, but for this talk, better to do this way. You remember this view graph. That was one of the very first view graphs I showed you. Just integral quantum Hall effect, quantization. This is the 2D surface, quantized Landau levels, etc. And then one thinks of all these other states in a way that is analogous to the fraction quantum Hall state. Sorry, to the integer quantum Hall state. See, the integer quantum Hall state is down here, and you get these oscillations from the integer Hall effect. Now we have another zero of magnetic field, so to say, out here at 1/2, where all the magnetic field has been eaten up. And if I slightly change the magnetic field, then I get a residual magnetic field, and these particles here that see zero magnetic field at exactly 1/2 see a finite magnetic field if you get a little bit off. And then they develop Landau levels, just like the electrons develop Landau levels down here. These new particles, composite fermions, develop Landau levels by themselves, and these Landau levels of the composite fermions become the fractional quantum Hall states. So you can look at the fractional quantum Hall effect also as the integral quantum Hall effect, but not of regular electrons, but of composite fermions. And there's a very nice symmetry. This is just the same plot, only once in red and once in black. And if I pull this over here, where put the 1/2 on top of the 0, then you see that the black zero minima, which are from the fraction quantum Hall effect, and the red minima, which are from the integral quantum Hall effect, are just on top of each other. So we should have seen this experimentally, but it was really the theorists that were pushing that down our throat. I suppose I have about 2 minutes. Is this correct? Okay. So this picture is now confirmed in many ways. There have been experiments done on these fractional states that then let you extrapolate back to some kind of a mass around 1/2. There's a lot of questions still associated. What's happening exactly at 1/2? What is the mass? What does it really mean? What kind of phenomena do you see there exactly? What else could you see? Is it a real Fermi system or not? These are all things that are up in the air and still experiments being done on it. But the concept of a composite fermion, composite boson, is really something that has become very important in the fraction quantum Hall effect. The spin of the electron has also come back in and became a very important tool to measure some of the energy gaps. I don't have time to get into it. We can actually associate a mass with these composite fermions. We can associate a G factor with the composite fermions. All this has been done over the past few years. Let me show you just one other state that is of great interest nowadays, and that's a state out here at 5/2. Never mind how I get to this. This is the 1/2, this is a 3/2. This guy is called 5/2. It basically means for every 5 flux quanta, you get 2 electrons. And this state looks sort of like this one, but when you cool, this state looks sort of like this one, but when you cool it down, it doesn't. And this is the newest experiments on that. When you cool the 5/2 state down, sorry, it's a bit busy. It goes to 0 and it gets a plateau. Now this is a half state, so it has an even denominator. So it should be a fermion, and fermions do not show a fraction quantum Hall effect. Composite fermions do not show a fraction quantum Hall effect, but they show a Fermi surface. This one shows a fraction quantum Hall effect. Was discovered in '87, I think, Bob Willett et al. And that was a big surprise. An even denominator became a fraction quantum Hall effect. How come? We still don't know. Well, let me actually point out, this is the lowest temperature you ever have cooled down an electron system. These data were just taken at the magnet lab in Gainesville, where they have very low temperatures, microkelvin for that matter. We use it only down to millikelvin in high magnetic fields. This is not that high, actually. This is only 3.7 Tesla. But we were able to cool the electron system down to 4 millikelvin, which is a real achievement. It's the electrons, not the lattice. This is the electron temperature. By various tricks that the people at Gainesville, Zhang Jia, and then together with our student down there, Wei Pen, developed that really let us do this. Now the speculation, and it still is a speculation of all, although the theorists tell us more and more that they're very convinced about this, and they even tell us that our data support it. I don't understand that argument yet. Is that what's happening is just like at 1/2, the electrons actually do form fermions. They take an electron, put 2 flux quanta onto it, and they are fermions. So now we are B equal to 0 with new fermions called composite fermions. But then they discover that they can actually mutually attract pairwise. This is an interaction in real space, but in fact, the wave function that you can write down for it, it's called a Pfaffian. I'm way out of my league here, but it's called a Pfaffian, but it's similar, it looks similar to a BCS wave function with an L equal to 1 in there. But there's an interaction in there, and they form pairs. And these pairs, sort of in far analogy with Cooper pairs, if you think of it, they can condense. They form a new quantum liquid now. So you form first fermions, then you have an interaction, it's just all Coulomb interaction, and they form pairs, and these pairs then open up a new gap, which is something like a superconducting gap. So in a sense, they form a new kind of superconductor made out of composite fermions, and that's what you see in the experiment. let me leave it at that. So there are various other experiments that are very other parts of the magnetic field scale. There are nowadays anisotropies that are being discovered in high magnetic fields. They're called stripe phases. There is the question, for example, how many electrons are required in order to see the fraction quantum Hall effect. Obviously, one is not good enough. I say obviously, but this is an important part. One is not good enough. It's a many-particle effect. And some people like Ray and others are looking whether 3 is enough or 5 is enough, or do you need 10 in order to see it. There's a weakness solid out there where electrons are supposed to condense into a solid of electrons, and that one, there are indications for it. There are things called skyrmions, which are many-particle spin systems that are playing a role. So this field is alive and well, to say the least. In fact, I believe the 5-half state, if we really can pin it down that it's this kind of a state, is really opening up a whole new universe of experiments that can be done. Let me show you my last view graph, and that is sort of where are we going. This is the data, or the result that Edwin Hall gave us about 100 years ago. Magnetic field, Hall effect, straight line. So this is just a standard Hall effect. And Klaus von Klitzen came along and told us that this is not so. There's actually, you see, this is a used U graph. I better fix it up. There's these big steps in here. This is the integral quantum Hall effect. And then Dan and I were so lucky to discover the 1/3 state, so suddenly there were more steps here. And then the 5 something came along, and the 7 and the 11 and the 13s and the 17s and the 23. And as we keep going, we're going to end up with that, which is a perfectly straight line. Only what you don't see is that there are infinitely many steps along here. It's called a devil's staircase, devil for obvious reasons. And there's going to be fractions all over the place. So eventually we're going to end up just like Edwin Hall is going to tell us, I told you so. So let me just show you this view graph here, which is probably the most important. All of this wasn't, I only changed pump oil. Of course, Dan, who's going to talk, long friend and collaborator, and really my mentor in many ways. Lots of collaborators, postdocs, students at Bell Labs that have worked on the fractional quantum Hall effect. And then there is particularly the people that are the crystal growers that are here pointed out in the all-important ones here in red, Art Gossard and Willie Wickman, and then also Lauren Pfeiffer and Ken West, who are growing the samples nowadays. So it was these people working on the fractional quantum Hall effect that really brought it all about. I always feel that Dan and I, we were so lucky to discover, it's a little bit like archaeology. We discovered the first tile sticking out from a roof out of the sand, and then it was all these terrific people that continued the work and really were cleaning up the whole, not cleaning up, actually discovering the whole building, which finally made us to receive the Nobel Prize for it. I feel like the luckiest person in the world, having been able to work with such terrific people and being part of this endeavor. So in a sense, I think I owe a lot of, not in a sense, I do owe a lot of gratitude to all of these people that have brought it about. I feel that I was only one of the lucky ones that was just there at the right time at the right place. Thanks very much. And of course, the right place at the time was sort of one street down the road.
Thanks for a beautiful overview. You don't get away so soon. Are there questions?
I don't want to cut into Dan's.
Mark?
Horst, could it have been done without the magnet lab?
No. Yes, of course. No, look, no doubt. We see the fraction quantum Hall effect now at 0.8 kilogauss, something like this, right? So this is exaggerated, but there's a few kilogauss. So yes, of course, today. But at this time, no. This sample, it required this sample, which was 90,000 mobility, and a field of whatever it was, 19 Tesla or something like that, where this is where the inflection was, to see it. At any lower than that, it wouldn't have happened. Nowadays, we have superconducting magnets that go that high. At that point, superconducting magnets were typically a Tesla, so one would not have seen it. Yes, at the point it required this sample and this magnetic field. A few years later, if actually it had been pursued any further, maybe people would have said, well, forget modulation doping, doesn't look interesting. But a few years later, you could do it at home, meaning in a superconducting magnet, but not at the time. Bob Laughlin.
Bob?
Horst, there are two prototypes I know about for the 5/2 state.
Mm-hmm.
And they're distinguished, so allegedly, by edge property.
By what? Edge state. No. This is edge states are always the next generation, right? I mean, you first have to get the bulk. Let me not call it bulk. You first have to get whatever we are doing, the trivial stuff, right, before you look into the edge states. Tunneling into the edge state is a difficult problem, right? You know, I mean, there's lots of question about what you really see when you chiral systems, et cetera. So I don't have anything. Maybe Dan is going to tell you something, but don't think. No, we don't have anything on the edge, no. I mean, the other thing to differentiate the two states is whether it's been polarized or unpolarized. And that's already a difficult one. That's the experiment that we want to do since a year, but it's so hard to turn a sample at 4 millikelvin electron temperature down in a high magnetic field and see whether one sees the lifting of the spin degeneracy. That, I think, is a trivial experiment, although it's very hard. And then comes the edge.
Why do they call the 5/2 state a superconductor when the longitudinal conductance it goes to 0? So is that just...
You know why. Okay, I mean, the analogy with superconductivity is a long one. There's lots of things that are different, but since it looks like it has sort of a character of the BCS wave function in there, so you can look at it as being superconductivity. But then, of course, everything else is different, so don't catch me at my weak points, okay?
Peter?
Yes? I don't think so. I mean, there is a description of these states here, a theoretical description. I think all the connections are not yet made. In fact, it was theoretically predicted that there were striped phases. Let's also keep in mind, there's a prediction of striped phases, something hard to read, and then there are experiments to show an anisotropy. So far, the connection that the anisotropy is due to striped phases had not really been made. We just think this is the area where there's anisotropy, this is the area where there should be striped phases, so probably that's what it is. One doesn't really know that. What has been discovered is anisotropy, but it's probably striped phases. From the point of theory, I think we got the experts in here. What?
Almost certainly yes.
Okay, this is one way. Patrick?
So was it back at this time in the magnet lab when you came up with Horst's first law that I teach my students all the time?
Horst's first law, I haven't heard about this.
The crummiest looking samples always work best?
Yeah, I guess I learned this from Dan in many ways. Right.
Okay, if there are no more questions, let's thank Horst again.
Well, it's a real pleasure to welcome Dan Tsui to MIT. Soon after he got his PhD from Chicago, then went to Bell Labs, where he spent about 15 years before he went to Princeton University as a professor in the electrical engineering department. I got to know Dan in the 70s when we were both in Bell Labs. And as some of you might know, especially that in those days, Bell Labs was known for having a bunch of very aggressive people around. Well, there are a few exceptions to this rule, and Dan is one of them. But Dan may not be the one who walks the fastest or talks the fastest, but when it comes to matters that count, it doesn't take long for one to figure out that he's usually the one that gets there first. I had experience, for example, in the late 70s when a lot of us were doing work on the localization, weak localization effects and disorder effects and so on. Dan was really very quick. He instantly understood the importance of what's going on, understood the theory, and he realized immediately that the MOSFET system is the ideal system to study these new theories, because he can control the electron density and everything else. So within a matter of a month or two, he and David Bishop came up with the experiment, the definitive experiment that showed all these weak localization effects and so on. And of course, the next great achievement was the fractional quantum Hall effect that we'll hear about. Since that time, I came to MIT in '82, and one of the great pleasures is to have periodic visits from Dan when he comes to do experiments at the magnet lab. And every time he would come and he would show me all these new data that he found, that he's excited about, that he wants to understand. But every time I talk to Dan, I always come away with the impression that he's someone who's really fascinated by nature, by what he's doing. He loves being at the frontier and exploring this new world, and he's someone who really wants to understand what he's studying. And to him, getting credit or being the first or getting honor seems to be secondary. These are things that would come naturally for him. Science is really what drives him. And so it's wonderful that this great honor has come to someone who really does not seek it. And so I present to you, Dan.
Thank you, Patrick. It is an honor and always a pleasure to be back on MIT campus. I think Horst probably would say, well, he was enjoyed it so much, even spent my first sabbatical in the magnet lab, in the Francis Pickering magnet lab. What I want to do for the talk is to take this opportunity to have a closer look of some of the long-standing problems as characterized by some of the questions and comments we use to hear very often. So more specifically, what I'm going to do is I'm going to give you a very brief, superficial overview, basically relating the other even denominator fractions, which Horst already touched upon. But before I go into that, any detail into that, those experiments, I'm going to spend some time tell you, say, tunneling experiment into the sample edges. And I don't think originally I thought I'll also go through some of the microwave absorption experiments in the very small fractional limit where the system, the electrons are insulating, are true insulators. And it's a, if you like, it's believed that, well, it is the putative Wigner crystal regime, but I probably will not have time to go into that. So this is what I would like to do. I have this view graph here just to remind me to say that in our modern day electronics world, and most device functions are performed by these two-dimensional electrons, which confine to move along the interface of two different semiconductors, or a semiconductor and an insulator. But the only point I want to make here is under normal ambient, these electrons behaves as just ordinary gas of two-dimensional particles. The strange or the extraordinary physics which Horst has shown us becomes dominant or very apparent when you take the system at low temperatures exposed to high magnetic field, and when the system actually is clean. It's a clean two-dimensional system. That's the point. But the other point I want to make is really the only reason I want to show that view graph before, actually. Let me put it back. In the magnetic field, the energy or the so-called Landau quantization quantizes the energy spectrum into discrete levels. If you like, they're massively degenerate discrete levels, and these levels are called Landau levels. And the point I want to make here is mainly the terminology I want to keep straight. So the Landau level index, this big N, is usually integers, 0, 1, 2, 3, large numbers, whatever numbers. So when you take the electron spin into account, each Landau level composed or has 2 spin levels. That's the only point I want to make, because we need to keep that in mind to look at some of the data in some detail. Okay, we have already heard from Horst's talk that in the so-called fractional quantum Hall effect regime, correlation is everything. And at the odd denominator fractions, which the system is going into the so-called Hall liquids, at the odd denominator, quantum Hall liquids, we have these fractional states you have seen. But also you have seen there's at even denominator fractions, correlation favors a normal metal-like Fermi sea of composite particles, or the composite fermions. And this is the case for the lowest Landau level, if you like, the n equal to 0 Landau level. And this is the data actually from very recent sample, Lauren Pfeiffer and Ken West grown on in September. And the data was taken by Wei Pan, who's a graduate student, Horst and I supervised. Yeah. And what you notice here, the filling factor 2 is somewhere here and down. So this is for the n equal to 0 Landau level. So there'll be two spin, if the spin split, there'll be spin up down here somewhere and have the spin down here. Okay, so in this level, indeed, the composite fermion is what the ground state for the even denominator fractions is indicated here. And for example, the 1/2, you have already heard from, Horst already showed you, except in this sample, because the perfection of the 2D electron system, this went up, I think Horst said is to whatever, 20, the denominator 21 or 20, whatever. And here similarly for 1/4. And the main thing is for the even fraction where the composite fermion is the ground state, the structure is essentially featureless and is flanked by two series. In this case, is the P over 4P plus minus 1 series of fractional quantum Hall states. And here, the P over 2P plus minus 1 series of fractional Hall states. And similarly for the 3/4 and 3/2. So for the n equal to 0 Landau level, indeed, the R denominator fractions are the fractional quantum Hall liquids. The even denominator fractions are these composite fermion states. For the higher Landau level, that's what I want to show here, and that apparently is not the case. The data looks very different. Again, here is the lowest Landau level, n equal to 0. You see at the even denominator fraction is essentially featureless. Just the fractional quantum Hall states converges onto this. The fractional quantum Hall state has this deep minimum and just converges into this even composite fermion, the ground state, the composite fermion gas state, essentially featureless. But when you go to the next Landau level, n equal to 1 level, that's for the 7/2 and 5/2. And you have deep minimum, which is very similar to the fractional quantum Hall states. And also these structures, on the flanks, on the sides, those are indeed the fractional quantum Hall states. Okay. Now, when you go to the next higher level, the index is n equal to 2, and you actually see a large spikes at 9/2, 11/2, and similar for the next level, n equal to 3, 13/2, 15/2. These actually have large peaks. But more importantly, whether they're a peak or a minimum, or a very deep minimum, depends on how you do the measurement. Depending on the measurement, the current is measured on what direction. The black is measured along this direction, defined as x direction, and the other one is the y direction. So this is basically what I'm going to do is I'll come back to show you more data, look at these higher Landau level, n equal to 1, n equal to 2, and in particular, just pick out the 5/2 and 9/2 to go through the experiment in some detail. But before I do that, I want to address basically the other comments you have seen is about the edge states. Halpern and 1, Selgang 1 product. sitting somewhere in the audience, I know, were the first told us how to think about these, the sample edges, how to think about the edge states. In case of the integer quantum Hall effect, it's quite easy to visualize or to picture them. And that's what is illustrated on this view graph. Okay. If this is the bulk material, in a strong magnetic field, we look at the one electron energy levels. They're just these Landau levels, separated by an energy gap, which is the cyclotron energy. Now, when I go to the surface, approaching the surface, sample surface, then when the electron orbit in the magnetic field, the electron feels the surface potential or the surface field, then it changes, it increases the electron energy. So my Landau level would have to be drawn in this way. So now if I am at the integer quantum Hall states, so my Fermi level is somewhere between these two levels. Below are all filled, top, or my n below n is all filled, my n plus 1 is all empty. Then, of course, inside the sample in the bulk is an insulator, it's gapped. But when come to the surface, there is state right at the Fermi level. And these states, or if you like, the electrons in these states are they consider one-dimensional electron system. And this becomes more clear on the next view graph, is in a real space, this is how it would look. This, of course, you would right away recognize this, probably a graduate student's thesis. Who else would do this? Need to think this is taken from Matt Grayson's thesis. As a matter of fact, the data I'm going to show you are all from him. So in the bulk, in the quantum Hall effect, the levels, all these cyclotron orbits all occupied. And the next higher energy level ones are empty. It's not shown here. But come to the edges, the edge states are just these so-called, in metal physics in the 60s, would call them the skipping orbits. These are the skipping orbits. And because of the magnetic field, they all skip in one direction. And the language, proper language to describe is saying a fancier language, their motion of chiral. They move in one direction. Okay? And this is for the integer case. And there has been a lot of experiment give evidence to this. Okay? For the fractional case, it's which you would have. For the fractional case, of course, again, in the bulk, it will be gapped. The charged excitation will have a gap. And the edges, electrons at the edges will constitute, again, a one-dimensional electron system, but it's interacting system. And it's well known that for one-dimensional interacting electron system, and it's the ground state is a liquid, and usually it's called the Lottinger liquid. Again, because the magnetic field is the chiral is called the chiral Lottinger liquid. And the main characteristic characterized Lottinger liquid is it has phonon-like excitation spectrum. So the density of states at the Fermi level, if you like, vanishes, but at finite energy excitation, the density of states goes over some power law dependence, as indicated here. Okay? And this would have direct consequences on the current due to tunneling either into the edge or tunneling between the edges. So if you look at the current, the tunneling current into the edge, fractional edge, or the tunneling current between the fractional edges. This will have direct influence, direct consequences. Okay. The earlier experiment on this is the Millikan-Ombach-Webb's experiment, where they look at the temperature dependence of the tunneling current between the edges using a point contact geometry. But what I'll do, basically showing the data Matt Grayson took, is following the tunneling, which is tunneling from essentially normal metal into the edge, which in some sense, many of you, I'll show you will become very clear if you just reminisce and, if you remember the normal metal superconductor junction in superconductivity, okay? So this is just repeat what I said already. So what I'm going to show you is the experiment Matt Grayson's data, and using the sample Lauren Pfeiffer and Ken West grown, this is the edge cliff overgrowth Ria Shuri mentioned earlier. The structure at the end is you have the two-dimensional electron system on this side, and the 2D electron gas is confined in a quantum well indicated here. Then from the edge cliff overgrowth, a tunnel barrier is grown, which is, in this case, be the aluminum gallium arsenide tunnel barrier. Then a very heavily doped semiconductor electrode, N plus gallium, which is just a normal metal electrode. So the experiment is to inject or tunnel electrons into the fractional quantum Hall system. That's the experiment. And if you remember from the normal metal superconductor tunnel junction, the classical Gave-Rall tunneling geometry, which you're measuring tunneling inject electron into this strong interacting system, the one-dimensional Latinger liquid system. And if you look at the so-called tunnel conductance, derivative of the IV curve, you will measure directly the tunneling conductance. Okay? So the experiment is just to measure the IV characteristic, the IV curve. And this is just another view what you have. See, this is for the 1/3 stage, the bulk charge excitation is gapped. So, and the edge, all the actions on the edge, that's the one-dimensional Latinger liquid. And the experiment just basically is measuring the IV characteristic. You expect a power law dependence. And the exponent alpha is basically, well, if you see the right, that's basically characterize this, the edge mode, the Latinger liquid. So that's. Wait a minute, I think, I have another picture. This is just a more realistic picture from Matt Grayson. This is a 2D electron layer, so you can put contacts, so you can characterize the fractional quantum Hall characteristics you set to characterize your sample. And here is the tunneling the normal electron injecting into that, okay? So you can look at the red curve is the IV characteristic, the Hall resistant characteristic of the 2D electron. And this is the 1/3 plateau. This is the 2/5. This is the 2/3. This is the plateau 1. And this is the tunneling IV. And if you look at the at the fractional 1/3 state, you would expect the Cairo-Latinger liquid, expect to have a Cairo-Latinger liquid, and the IV should have, you expect the power law dependence, and with an exponent, it's expected to be actually for 3. This is the first piece of data from Albert Chan's early experiment. And this is right at filling factor 1/3. We know the bulk is gapped, and the edge we expect to have the Latinger liquid. And there's more than 2 decades has a power law, clear power law dependence indicator, and the power is 2.7, is sufficiently close to the expected value of 3. Let me just what Matt Grayson did is he looked at a large number of samples. On each samples, he looked not only at the 1/3 or 2/3, also away from those. At a large, just continued various magnetic field, very close grid, look at it, how do they look? And surprisingly, when even you're not 1/3, I think it's the green, when you're away from the 1/3, you also have the same power law dependence. And in this wide range from 15 Tesla to 7 Tesla, you all have this power law dependence. As a matter of fact, this power law, this is semi-law, this is a law plot. This power law dependence would cover basically about 4 decades. So I think range is certainly unambiguous, and the next few view graph, I just flipped them very quickly. It's just the fit it made. The fit is to a theory. Well, you can use just a resistor network be the same way. This is the fit is fit with Shaman Freckens theory. This is right on 1/3. His fit gets 2.8, where Albert Chan had earlier 2.7, and this is in the higher field end. The fit again. This is about 4 or 5 decades. It's about 4.2 that fit, and again you're away from the. I'll just very quickly flip to give you some sense. The fit really. This is probably about 3 decades or so, and that give a power law about 2.5. And this one probably narrower range, but still, no, it's not. It's still about 4 decades, give you about 4. So I just want to mention what I want to show is if you take all his data from the power law dependence, the exponent is alpha, we use, and all the data plot them up is from these 4 samples. These circles are Albert Chen's early data. They essentially all follow roughly this straight line. Okay, it's I mean, the immediate first surprise, surprising, is you know, when you're away from the plateau region, away from the fractional quantum Hall states, the bulk is not gapped. The bulk, you know, has conduction, but the edge state, you know, the Latinger liquid picture, the edge mode, which are Latinger liquids, are still, you know, just proper description of it. Okay, and the other one, of course, this is the dashed curve. It's a theory from Scheitall, Levertov, and Halper. And this, the discrepancy between experiment and theory, I think it still remains a problem. The other point I want to just mention that for the filling factor 1 and higher in this region, it's expected the edge mode, the edge channels are Fermi liquid. And the exponent is just, you know, your normal IV curve, normal omega, and it's just expected to be 1. The more recently, Michael Hilke was a postdoc at Princeton, looked into basically between 1 filling factor, 1 to somewhere here, has just blown a lot more data. And indeed, this flatten out to 1 occurs earlier, but indeed is continued. But his sample, or the sample he looked at, the data to date is not, basically it's not good enough to say anything about what about the composite fermion ground state at 3.5, or the 5.5 at those particular fittings. Okay, that basically is all I want to say in relation to tunneling into the edges of the fractional quantum Hall effect systems. Now I would like to come back to the even denominator fractions in higher Landau levels. In Landau levels, for the Landau index n equal to 1 and higher. Okay, this is Laureates data, which is on samples actually Lauren Pfeiffer and Ken West grown in, I think it's 1991. These data are early, 92 or so. But the point I already mentioned, if I look at the 5.5, there's clear minimum. You know, it's very different from the 5.5, very different from what you've seen, you know, 1/2 and 1/4 for the composite fermion signature in the data. But more strikingly is when you go to 9.5 and 11.5, which is for the Landau level index n equal to 2, for the 9.5, 11.5, 13.5. and they give a sharp, very large resistance peak, very strong resistance peak. And depends on the current orientation, which direction you measure the resistance. In the 90-degree off resistance direction, it's a deep minimum. And in order to be able to go through the data later more, it's kind of confusing once I tell the magnetic field. I want you to keep in mind two things. One is these lines, vertical lines, indicates the easy conduction direction. If you measure the current in that direction, as in this case, the resistance does not have resistance small. Okay? Perpendicular to that direction is a hard conduction direction. So this is measured at perpendicular. And the hard direction is the x direction. And the easy direction is the y direction. So that's one point I want you to keep in mind, okay? The other point is, in addition to this sharp peak, there are also other structures. And these structures, they don't fit the fractional quantum Hall scheme. They don't fit as 1/3 or 2/3 or 2/5. That's what. And when the temperature goes, when you lower the temperature, that's indicated here, then everything disappears, just the spike for this current direction, this spike dominates, okay? And in addition to that, because I want to mention, this is, samples in the almost a decade ago was that, and the samples are grown in those days are not rotated, so you can have some very very density gradient, some very small. In this sample, the density gradient is sort of about or less than 1% in this direction. But I think really look at it very carefully, it's very convincingly, this anisotropy, the difference, cannot be attributed to this slight density gradient. Okay. But I'm going to show you the data on the next view graph from Jim Eisenstein in Caltech, Lilly and Caltech. Those are samples were very recently grown, they're rotated, and there's no non-uniformity. The result is essentially the same. But before I do that, let me just also say two other points. For this sample, the sample plane is 100. Roy made the X-ray diffraction very carefully. The orientation is better than 0.05 degree. And these edges of 110, they are cleavage edges. You cleave them, they're just essentially right out. Okay. These are the few things I want to mention. With that in mind, well, first let me just show you the data from Lilly et al., which are more recent samples in terms of the 2D electron quality, 2D electron system quality, but the data is essentially the same. Okay, in one direction, it's large resistance, the other direction is minimal. Okay, and in Lilly, and they also look at the different orientations. The data, you have seen before is essentially the current measure along the two different 110 directions. Whereas here they also H1 rotate the sample by 45 degrees, and you still see some anisotropy, but it's much smaller. So this experiment actually pinned down, located what the anisotropy direction is. Okay. Now, with this in mind, now I want you to just stare at a few foils to go through the overall. First, this one is a temperature characteristic. So the anisotropy is basically, well, about 115 millikelvin is isotropic, so there's hardly any difference. The anisotropy started basically about 100 millikelvin, and it becomes stronger and stronger. That's one point. And the other structures I already mentioned that they don't fit any fractional Hall states. Okay? And this data curve here is the Hall resistance. The Hall resistance has structures in this region. Basically there's some, at the lowest temperature, I think is the solid line or something. There are clear structures, but so far, we haven't been able to identify the structures for any, clearly identify the physics. The next view graph is just a summary of this one. Just plot the temperature dependence. This is for the 9.5 maximum and minimum. They're essentially they're the same isotropic at about 100 millikelvin. By about 60 millikelvin, they essentially saturate the growth. And this is just plot the structure on the side. It does not really fit any fractional states on the side, which is for these two different orientations, okay? For the two different current orientations. That's basically the main data and the features I want to show you. The application of an in-plane magnetic field has a very large effect on this anisotropy. That's indicated here. I probably should this is the one, let me look at it first, okay? It's indicated here. If I apply a magnetic field this is the in-plane field. I apply a field in the plane of the sample, okay? And this is the in-plane field. If the in-plane field is applied in the this is in the easy conduction direction. That's the y direction. If I apply it in the easy conduction direction, it suppresses the resistance in the hard conduction direction. In the hard direction, the resistance 9.5 large becomes small, small, very small. At the same time, the easy conduction direction, the resistance getting larger, larger, then getting very large. If you like, this put an in-plane field in the easy direction, now changes the easy conduction direction to the hard conduction direction. And the hard conduction direction changes into easy direction. I know it's confusing, that's why. What's basically what I'm trying to say is basically, I'm trying to say what the data tells you this. An in-plane field makes the transport along it hard, makes the transport along the in-plane field direction hard. If you put a large in-plane field, at the end of the day, the easy conduction direction is perpendicular to the in-plane field. That's really all I'm going to say. Now, yeah.
Does it go back? You take the field off, the in-plane field off.
Right.
Does it go back to the way it was before?
Right. There are no hysteresis. It does go back, right? And this is consistent. Well, in some sense, once you look at this one, which make it that conclusion, I think, even more clear. See, this, of course, you put the field already in the hard conduction direction. So in some sense, the things already line in the right direction. At the end, actually, you don't change anything. But in between, it changes things. So at the end, when you put an in-plane field, put a field in the plane, the in-plane field orients the system in such a way at the end, the easy conduction direction is perpendicular to the in-plane field. That's the message I want you to take away with. That's really big. That's what the experiment says. Okay? The growth part of the experiment, that's what it is. Okay? Now the experiment, of course, has much more detail. You know, all I'm saying at the end. So at the end, if you start out with a line in the right direction, the in-plane field's perpendicular to the easy conduction, at the end, nothing changes, just amplitude somewhat. And if it's the wrong direction, they switch. Easy becomes hard, hard becomes easy. In between, there are definitely more than that. And later, in some sense, you can feel, well, that probably is reasonable. You put an in-plane field, you know, not only you do some kind of anisotropy-related thing, but you also change, you know, the Zeeman energy, all kinds of things, okay? But the main thing at this stage I want us to, you know, keep in mind is that this is just the same thing, just plot in an anisotropy, the, you know, difference of the resistance in the true direction normalized by the sum, okay? But the message really is that you put an in-plane field, and that field, you know, forces the system into such a condition, the easy conduction direction is perpendicular to the magnetic field. Okay. Our current understanding of it, or at least that's what what I hear people telling me is this so-called strive phase. The understanding of it, you know, has to go back to Shklovsky and his collaborators. Earlier, this paper on, and also Bolson and Chalker on the Hartree-Fock calculations for the ground state of the 2D electron system in a magnetic field. What they find is they find for Landau index bigger and equal than 2, and a charge, a unidirectional, this U stands for unidirectional charge density wave state, is favored over the fractional quantum Hall state. I have a sort of a cartoon of a picture here, just try to give you some, you know, rough flavor of what all those big words mean. In some sense, what it means essentially is that the possibility when you're at 9.5 filling, the system phase separates. It separates filling factor 4 Hall state and filling factor 5 whole liquids, 4, 5, 4, and these stripes. So if I look at the 2D density, and they basically, this was a density wave, this is my periodicity. That's really, that's the only point I try to convey with this. Very recently, I think, it must be too late. I got lazy, didn't write. It's Jungwirth, I think it's McDonald, Gervin, and Smirka. They have calculated the anisotropy energy when you put an in-plane field. And they find is that the in-plane magnetic field tends to align the stripes perpendicular to it. So in the, let me go back to this picture. What their finding would say, they will, if the stripes in this way, the in-plane field, you put an in-plane field, at the end of the day, the in-plane field will tend to align these, the anisotropy energy such, align the stripes perpendicular to the in-plane field. And in that sense, in a sense, well, since we don't have a transport theory, we don't really know how to think of transport, but it just in this phase separation, you would say, in this direction, I try to indicate these are the edges. There's, for 4, there will be a lot of 4 edge states, and these edge states can, they're compressible, and the bulk are incompressible. Yeah. So these certainly is the easy conduction direction is along the stripe. So the magnetic field tends to make the easy in this picture for this stripe model, stripe phase model, would align it perpendicular to the magnetic field. In that sense, it's consistent with the experimental observation. Okay. So qualitatively, or the main features of the experimental data is consistent with this stripe phase picture. Of course, to relate more qualitatively to the experiment and also the more detailed structures, we'll need a transport theory. In particular, how do you transport charge in this kind of model across the stripes? In addition, in the Hartree-Fock model, there's also, in addition to the stripe phase, there's also bubble phase. So, can one attribute those additional structures in the region other than the peak, away from the 9.5? Can one attribute that or assign that to for example, the bubble phase? I think we have to wait and see. Let me see how that goes. Probably okay. Let me the next part. Let me just mention. Go back to the n equal to 1, or the 5/2 even denominator fraction. That Horst has already pointed out in his talk. Let me go back to this earlier data you have seen. I think Horst has also. basically, I want to remind you is for 1/2, same 3/2, earlier we saw quarter essentially. The composite fermion signature essentially is just a very broad minimum. But this is the data in 1987, was mentioned. But if you look at a 5/2, this structure, the minimum, is much stronger than was expected. The more detailed result, the more detailed experiment was on this view graph. When you change the temperature from 100 millikelvin to the lowest, about 25 millikelvin, this minimum definitely becomes very strong. It looks like it certainly is not, very different from the composite fermion signature at 1/2 or 3/2. And when you look at the Hall resistance, that's this data here, and it clearly shows clear deviation from the classical Hall law. And this certainly strongly suggests the 5/2 is, or the 5/2, could be or may be a fractional quantum Hall states. The more recent data you have seen already, Horst has shown, these are the data using the microkelvin facility in Gainesville. This Horst already mentions Wei Pine and Sha in Dwight Adams' microkelvin lab. And the experiment, here's 5/2, clearly shows you are indeed cooling the electron temperature. So the electron temperature is being cooled, very, very clear. Okay, that's one point. But I'll not dwell on that. Let me just mention that once you cool the temperature, go below the temperature to at the lowest temperature indicated here, and there's a very clear plateau developed. And the plateau is quantized to the quantum number 5/2, just essentially using the 2 and 3 as a calibration. And as calibrate against them, those is quantized accurately to better than 2 ppm. The limitation is just, didn't really, it just instrumentation wasn't designed for better quantization. So this clearly says the 5/2 state is indeed a fractional quantum Hall states. It's indeed an incompressible fluid state. At the present, there are 2 candidates, or at the present, or I should say, throughout the years, there are 2 candidates for the ground state. What is the ground state? One is the singular state of what usually is called a Haldane-Rezai hollow core type. It's basically the interaction potential has this particular hollow core model. One is this model. Okay. And the other one is the Fabian state. Whenever you have so many F's, but Horst already mentioned the Fabian, which really is a p-wave pairing of the composite fermions, Horst 1, 2, some detail of the BCS type of condensate. Okay. The early support for the experimental support evidence, or evidence not, the support from experiment in the early days for this singlet state is the total magnetic field experiment. See, one way to view the total magnetic field is, since the electron system is two-dimensional, indicated here, you can increase the total magnetic field without changing, or put it the other way, keep the perpendicular field constant and still increase the total magnetic field. Of course, the fractional quantum Hall correlation, the correlation gives you rise to the fractional quantum Hall state in the polarized. In the simplest case, it just, well, actually, is the given by the, or the, put it simplest, it's a perpendicular magnetic field. Okay. Whereas the Zeeman energy is related to the total magnetic field. So by tilting the magnetic field, essentially, keep the perpendicular field constant, you can, one of the simplest way to view this, the only thing, or you do nothing to the system except you're changing the Zeeman energy. That would be the simplest way to view the total field effect. So if you do that, view it that way and do the total magnetic field experiment, this is what you find. This is the earlier data from Jim Eisenstein and Bob Willett. This is a zero magnetic field. You have very strong minima at 5.5. When you total magnetic field, that minima decrease. As you increase, when you total it, you increase the total field. Basically, this happened, the total field earlier is 4-some Tesla, now it's 5-some Tesla. But the perpendicular field is the same at this point. Okay, it's 4.8 Tesla. And by the time the parallel field, or the Zeeman energy, increased to about 5.7, and it's very weak. By the time more than 7 Tesla for the total field, or the Zeeman energy, then the 5.5 structure disappear, or the 5.5 state is quenched. This, in some sense, was the strongest support for the singlet state. But very quickly, the more recent experiment makes this, certainly show there's problem with this. It's not as with the singlet state. One is shown by this data here. For this data, the 5.5 is still equally strong and appeared at about 12.5 Tesla, almost 13 Tesla. That's a very large Zeeman energy. So that's one problem. I think the more definite problems of this sort of suggests maybe the singlet state, there's something not right. And so the other problem came in some sense, became clear more recently. That's the totem field experiment. You have already seen the totem field in relation to the 9.5. Now it's essentially the same experiment, same tilting experiment. I just look at the data at 5.5. Okay, well, if you look at the 5.5, in this case, the in-plane field is put along the hard conduction direction, the in-plane field. Okay, the hard conduction direction is for the 9.5. For 5.5, it's isotropic anyway. But now you put an in-plane field. Once you put an in-plane field, then you see they become anisotropic then depending on what direction you measure. Eventually, when the in-plane field is sufficiently large, so one direction becomes hard conduction, the other direction is the easy conduction. And this is when the in-plane fields in the hard conduction direction, okay? Now, if you put the in-plane field in the other direction, again, it's the same thing. At the end, when the field is sufficiently large, then the system becomes anisotropic. The 5/2 in the easy conduction for the 9/2 easy conduction direction becomes a large resistance, difficult to conduct. The other direction is easy to conduct. So the main message here I want to say is you put an in-plane field now, or do a tilting experiment, but keep on tilting even higher, right? Then you find out the system is anisotropic. So what you have seen earlier, just the suppression of the minimum, that's only part of the story. So after you keep on tilting, it's not only suppress, the orient disappear, but if you're in the right direction, actually measure in the right direction, you get a maximum instead of minimum. Okay, that's really the main message. The other is just put this data, since have all the data, so plot it out. Okay, that's really the main message. And somewhere here, okay, this is the same again. It's with that. This is just, let me just not even bother. That's just the plotted anisotropy. But I want to show you this is the data from Lillian Eisenstein from Caltech. It's same result. Let's put it here. It produces strongly anisotropic transport on the 5/2 when you put the magnetic field. So what the experiment says, or this experiment tells us, is that the dominating effect of the tilting experiment, the dominant effect, is not the Zeeman energy. The dominant effect is the in-plane field induced anisotropy. It's this anisotropy energy we see in some of the, the Hartree-Fock calculations indicate. Okay? So the dominant effect is the in-plane field induced anisotropy. It's not the Zeeman energy. So the in-plane field, what it does, it destroys the it destroys the 5/2 fraction quantum Hall effect states. And in its place, it creates if we use the 9/2 state as a guide, or if we believe the 9/2 state is a unidirectional charge density wave state, ground state, then it creates a unidirectional charge density wave state. That's the stripe phase state. And the experiment you see, the tilting field experiment, which you really see is a phase transition from this Fafian state, or P-wave paired state of the BCS type, to the stripe phase. And this transition is driven by when you apply this in-plane magnetic field. There's a preprint. I think I have there are two preprints. One has 3 names, 1, 2. I think it's the one Rezaei and Hao Dan. Their calculation is a finite number, a certain number electron calculation. Their calculation sort of showed that for the spin polarized system, and essentially the Fafian state energy and the stripe phase energy are very close together. So they would say, if you can change the interaction potential some way around, it's very easy to change it from one to the other. Okay, that's right. Okay, I think yeah, my time stopped. I have already said I will not say anything about. Okay, let me just say, read these few words, then let me stop, okay? What basically I was going to say this. The picture that has emerged from a recent experiment is that the states of a clean, I sort of emphasize a clean two-dimensional electron system in magnetic field at fractional fillings for the Landau levels 1 and 0, means the first 4, if you count the spin levels. For Landau for filling factor nu roughly bigger than 1/6, you have the fractional quantum Hall liquids at the R denominator fractions. And the even denominator fractions, you have this composite fermion gas, if a composite fermion Fermi liquids for the lowest, in the lowest Landau level case. For n equal to 1, for 5/2, what you have, very likely, I think, so it's p-wave paired composite fermion liquids. Then for n bigger than 2, the higher Landau levels, it appears, I think, the current data sort of indicates the Hartree-Fock ground states has a lower energy than the fractional quantum Hall states. I will not time to say anything about the Wigner crystal, but it's believed in the clean system for the filling factor less than 1/6. There's the Wigner crystal stayed out. But in real life, of course, the physical phenomena we see are always interplay, the results of interplay between disorder and the electron-electron interaction. It turns out in this Wigner crystal case, or in that regime, the disorder becomes very important. And disorder at the present certainly is one of the most difficult problems. And we really don't know how to or characterize right now. I better stop here. Thank you.
Well, thank you, Dan, for the very current update on this exciting story that obviously is still ongoing. There may be time for just a quick question from the audience. Okay, since we are running late, maybe we should just move on. Let's thank Dan again.
So now I'm going to give John Joannopoulos the joy of introducing Bob Laughlin.
Thank you, Mark. It is indeed with particular pleasure and pride that I introduce our next speaker, Bob Laughlin. As I'm sure many of you know, Bob's talents, his brilliance and creativity as a theorist have by now become legendary. But what you may not know is that some of these talents actually overflow into other areas, such as music and art. It turns out that Bob is an accomplished pianist. He is also a composer of classical music. He's written 4 piano concertos. He's also a skillful sketch artist and a very clever cartoonist. You can find some of his work on the web, on his homepage. Actually, some of my favorite cartoons are jibes at the National Science Foundation, which Bob calls the National Seance Foundation. And in the first 2 talks, we saw that some very beautiful and pioneering experiments led to the discovery of a new 2-dimensional electron system with some very unusual properties. And of course, now the question was, how can one account for these experiments? How can one understand what the nature of this system is? Now, interestingly, historically, fascination with 2-dimensional fluids actually dates back to antiquity. The first written record that we know of appears in Babylonian cuneiform, about 4,000 years ago, about the times of Hammurabi, and describes a kind of divination known as lacanomancy, where the diviner, or the baru, as he was called, would drop little droplets of oil into a bowl of water, and then would very, very carefully study the nature and intricacies of this expanding film across the surface. And in doing so, thereby prophesy the fortunes of kings. And so it came to pass that it would take a modern-day baru, Bob Laughlin, to decipher the nature of the intricacies of this novel 2-dimensional electron system and lead to really what is a truly beautiful theory of a new state of matter, a novel quantum fluid with fractional charged quasiparticles. And so please join me in giving Bob a very hearty welcome back home.
It's always a pleasure to be back here at the place where they number the buildings. I was many times in this wonderful lecture hall, not listening to physics, listening to music mostly. MIT's music program is obviously very special. I remember vividly hearing Murray Gell-Mann here confuse us all about quarks. It was at MIT that I first heard Ray Dingle talk about heterostructures and all the amazing things they could do demonstrating elementary quantum mechanics. I later heard some great stories about Ray from Horst, and I hope any of you that put enough liquor in him will get those stories out. Now, yeah. I apologize for this lengthy, wordy thing, but I have a point to make this afternoon that is summarized succinctly in it. So it is about my story of why the fractional quantum Hall effect is important. It's fascinating for lots of reasons, but it's important, in my view, because it shows experimentally, this is the key word, experimentally, that both particles carrying a simple elementary fraction of the electric charge of the electron and interacting by gauge forces not postulated in the underlying equations of motion, can arise in an emergent manner as collective effects from ordinary particles obeying the ordinary laws of quantum mechanics. Now, both particles carrying fractional quantum numbers and powerful gauge fields between them are key postulates of the standard model of elementary particles, something that is allegedly fundamental in our universe. And as I'm going to claim this afternoon, the importance of these experiments is that they impugn this idea. They suggest that maybe such things in the universe itself could be emergent, which is to say, could not necessarily be fundamental at all, but just collective phenomena. Frank Wilczek has a wonderful name for this. He calls it solid-state imperialism. And I am the worst of the solid-state imperialists, at least I hope so. Now, on that note, let me start off with a thing that's been a lot in the news lately, which is the theory of everything. Now, this is not the theory of everything because there is no light in here, and there is no nuclear physics in here, and there is no gravity in here, and there are no weak interactions in here, and so forth. But for chemistry and the world of physics at people scales, this might as well be the theory of everything. And what I mean by everything is shown down here. Now look, everybody, I apologize. I made this view graph in Stockholm the day after we just had a press conference that was completely monopolized by Professor Sen, who won the Economics Prize. And he had, of course, done fundamental work in welfare policy. And you can imagine that nothing sells better in Sweden than talks about welfare policy. And so I was feeling my oats here when I finished out the things that the theory of everything could describe. Okay. Notice what went by Ebola virus. Right. Okay, now, one of the things that these, oh, by the way, those of you who are not physicists, what is this? This is the elementary Schrödinger equation for non-relativistic matter. And H is the equations of motion for this matter. It consists of kinetic energy of electrons, kinetic energy of ions, Coulombic attraction between them, and also Coulombic repulsions between pairs of light particles. And that's it. Okay, now, one of the things that this theory of everything describes, it is alleged, is this experiment. This is not von Klitzing's original quantum Hall experiment, but it's conceptually the same. So let's talk about it as though it were. So let me remind everybody that the way these experiments work is electric current is forced along a sample that's typically about 1 millimeter, or on the order of several millimeters in size. In fact, this distance here was 1 millimeter. In the presence of a big magnetic field pointing out of the board. Then one measures 2 voltages. This one between this pad and this one, between those 2 pads, that's the wiggly line here. And also between this pad and that one, and that's the line with the stips. And those voltages are measured as a function of field strength, magnetic field strength. And what the effect is that at certain values of the magnetic field, or more precisely, certain ranges of it, the potential drop in the direction the current is going dies away to nothing. And at the same time, the Hall conductance, which is across the current path, becomes constant. And what Klaus discovered was that the value of this constant, which you can measure accurately because it's constant, is related to the current being forced by a Hall resistance that's multiples of elementary constants. In this case, the electric charge of the electron and Planck's constant. Now, as of this moment, the accuracy of this experiment is about a part in 10 to the 8th, slightly less. And I ask you all to ponder how accuracy that big could come out of these equations. You see, everybody who's studied quantum physics knows that computing things like air, water, and fire from this underlying equation of everything is a ludicrous undertaking. It's too hard. The equations here cannot really be solved accurately when the number of atoms exceeds about 10. Accurately means a part in 10 to the 4, maybe. Okay? So beyond that, it isn't possible to solve first principles solutions. So when we get elementary constants, Planck's constant and E, coming out of a measurement with 10 to the 20th particles in it, we have to pause and ask why. Why is it so accurate? Certainly, you can't deduce this starting from the underlying equations. That's too hard. Now, you all may or may not know, accuracy of this kind occurs all the time in physics. The first examples actually come from chemistry, the ones I like to cite. Electrochemistry turns out to be a very accurate way of measuring the electric charge of the electron. However, the sexy physics examples mainly come from superconductivity and the Josephson effect. The Josephson quantum of magnetic flux is the most accurate quantity known in mensuration, aside from the speed of light itself. And so there's plenty of precedent in the physics literature for many, many particles giving rise to accurate measurements of elementary constants. And in all those cases, we know the reason for this accuracy is higher organizing principles. The matter itself is acting in some collective way that you cannot deduce from these equations. You can't go deductively from these equations to this behavior because the accuracy isn't there. So the intellectual problem that's posed by questions like this is, what is the principle? Why are these experiments so accurate? Now, apart in 10 to the 8, you begin to think about this a little bit, and you see that, well, the theory of everything that I showed you actually has corrections. It has corrections. The biggest one is here. As all practical purposes, that spin-orbit coupling and things of that sort in this material would be parts in 10 to the 4 effects. The radiation field actually is bigger, but it's subsumed by renormalization effects in QED. However, once we begin to worry about these things, then we begin to worry about all the other possible corrections to the experiment. How accurate can it get? What is limiting its accuracy, if anything? Now, there is an idea that is well known to people who worry a lot about the quantum mechanics of empty space, and that is that empty space isn't empty. Empty space is full of stuff. That is the sum total of the accelerator experiments that have been done since the Second World War have told us that space is a lot more like a piece of glass than it is ideal Newtonian vacuum. It's filled with stuff, and so when I talk by analogy between issues that we have in the vacuum of space and issues that happen in solids, in fact, this analogy is apt. Empty space is not empty in exactly the same way that a solid is not empty. So all these corrections to the laws of physics in ordinary space matter. At least in principle they matter, and one of the questions we have to ask is, why don't they show up in mensuration? Why are all these little corrections to the underlying equations irrelevant? Okay, now, the answer, of course, is there's a principle involved, and in order to talk about this principle, I have to remind you all of something you know, or teach you it if you don't, and that is something we call the principle of adiabatic continuability. So here's the problem. Suppose we've got something we want to understand, and it's very complicated, but like, for example, the Hall conductance, but we know there's a principle involved that makes it exact. So we can imagine a thought experiment where we perturb the equations of motion slowly and interpolate between lambda equals 0, which is the thing we're studying, and lambda equals 1, which is some idealized limit of the problem. Then, if it turns out the thing we're measuring is constant, as I adiabatically deform the equations of motion, then I can understand what's going on over here by studying what's going on over here. Solid-state physics, we do this all the time without calling it this fancy name. We call it modeling. But I have to be a little careful now because the thing we're trying to understand is an accuracy. And so we can't be cavalier about modeling and have to really think hard about what continuation principle allows us to understand something exact in terms of a model. Now, the model that we like, I would say, let's say the model would be, I guess, this end of the line, that we like to think about this problem in terms of is the one shown here. So what this is ordinary non-relativistic electrons feeling a magnetic field, B, and also moving in what we call a dirt potential or a random potential. Now, at the risk of telling a joke that will bomb, the dirt potential is like pornography. I can't define it, but I know it when I see it. In this case, the random potential is something that we could sketch, but truth is that in physics we don't know how to define a random potential. We only know how to define the behavior that you see in one, right? And the behavior that you see in random potentials has a name. It's called localization. And localization is an emergent principle that we know to be true because it's been seen in experiments many, many times. Now, before we get to that, let's look at this. This random potential, it turns out, is crucial to having Hall plateaus. It's very easy to show that if it's missing, then you don't have them. So suppose, let's do that. Suppose the system is translationally invariant. So we have some density of particles in there and a magnetic field. Well, then you all know you can run past it, make a Lorentz transformation. Then by the relativity principle, there will be in the moving frame an electric field across the sample, a current going along the sample, and the ratio of the two after some algebra turns out to be the number of particles per square centimeter divided by the field strength times some elementary constants. So measurements like this, Hall effect measurements, usually measure the particle density. And in fact, this is a standard and rather boring experiment that one does in semiconductors to tell how many extra carriers you have. A corollary of that idea, then, is that the quantum Hall effect can't occur in samples that are perfect. Because if the sample were perfect, it would be measuring the number of carriers in there, and the number of carriers in the sample is not quantized. Now, let me now tell you all about localization. This, unfortunately, is confused by dimensionality issues, so let me tell you the old lore. Back in the old days when people were thinking about three-dimensional systems, semiconductors in particular, the idea of localization was born. It was born in the mind of Phil Anderson. The basic idea of it is that eigenstates of one-electron quantum mechanics, which is what we're talking about here, come in two varieties. There are extended states and localized ones. Extended states are contiguous from one side of the sample to the other, and they are capable of carrying electric current. Localized states are the opposite. They are not contiguous from one side of the sample to the other, and they are not capable of carrying electric current. Now, in an actual sample, it is found experimentally that not only is this true, but there is an energy scale called the mobility edge, below which all the states are localized and above which all the states are extended. And the way the system approaches this edge is part and parcel of the metal insulator transition in disordered one-electron problems. Now, there was, in the old days, lore about this, that you couldn't have localized and extended states at the same energy, because if you did, then the tiniest amount of perturbation would mix them, and you'd have two extended states. But nobody knew whether to believe that lore or not, so the way it came down eventually was that this was adopted as true because the experiments told us it was true. Localization is a phenomenon that happens in nature that you cannot deduce from microscopics. You can get part of the way there if you cheat and make some assumptions about what a random potential is. But the truth is we don't know how to do that. So the right way to look at localization is not as a theoretical idea so much as an established experimental fact. Now, what happens in a magnetic field? Well, at the time of this experiment, nobody knew. Nobody knew what should happen. And there were some things we did know, which was the random potential should have taken Landau levels and broadened them. Landau levels are highly degenerate manifolds of states. And the first thing a perturbation does to degenerate states is it breaks the degeneracy. So everybody expected the density of states of this one-electron problem to look something like this. And actually, I think it's fair to say in the beginning, everybody expected everything to be localized. That it should have been localized in the tail region was completely obvious from anybody's point of view. That there should be localization in the center was very non-obvious. The Klitzing experiments told us that it was not so, that there were extended states in the centers of these Landau bands, and the reason is because it conducted electricity. So we knew that it must do so, so there were extended state bands there, but we didn't know much more about that. In those days, it was 1 year, no, I guess more like 2 years after the publication of the famous Gang of Four paper, predicting or asserting that localization must be complete in 2 dimensions, and we are in fact in 2 dimensions in this problem. So many people felt that localization should have been complete and something else must have been going on. Now, as I said, the experiments told us otherwise, and now in the light of hindsight we understand that localization physics is different in magnetic fields than it is in their absence. And in particular, this problem has a density of states which actually looks like I've drawn it. It's tails of localized states separated by distinct bands of extended ones. Now, how do you get perfection out of imperfection? This is relevant to the fractional quantum Hall effect, so let me lead you down to this idea historically. Here is this now infamous argument due to me, which accounts for why localization makes exact quantization of Hall conductance. And as Horst said, the essence of it is that the system can be made by a thought experiment into a charge meter. The thought experiment which does that is illustrated here. So we imagine wrapping the quantum Hall system into a loop. There's a magnetic field coming out of the surface of this loop. I don't know how you do that, just do it. And we will imagine filling up these 1-electron states up to some chemical potential that is in the localized state band. Now, rather than computing currents, which is hard, let us compute energies and then take the adiabatic derivative of the total energy of the system with respect to a little bit of magnetic flux that's poked through the center. This is not hard to understand. It's just Faraday's laws of induction. When you change the flux through the center, there is some EMF that winds around the loop, and if there's current going, then it'll do work on it. Why is this allowed? Well, it's allowed by the fact that the system doesn't dissipate. So that if we are in a region of localized states, then the conductance, which is to say the dissipative part of the response function, has to be identically 0, because localized things are insulators. And so that means that this flux can be put into the loop and out adiabatically. So it's because there's no dissipation that adiabatic derivative makes sense. Now, while one is doing this adiabatic derivative, the localized states do nothing. And the reason for that is that since they don't go around the loop, they can't tell the difference between addition of flux and a gauge transformation. So it's exactly true that the localized states contribute nothing to the adiabatic derivative. And for that reason, I can just erase them, which I've done here. Now we've got a much nicer problem, which is little bands of states separated by finite gaps in which the chemical potential lies. Now, as I do this adiabatic derivative, it is not possible for a state to cross the gap adiabatically. The reason for that is that if it did, it would be coincident in energy with a localized state, and therefore would have to be localized. So that's out. So this little localized state region here is like a brick wall. It prevents adiabatic motion of states. And so that means when I wind the flux, the only state motion that's allowed is from one edge to the other. Now, the trick to making this calculation simple is to make the sample big enough that the adiabatic derivative can be replaced by a differential where the denominator is a flux quantum. Doing this means that adiabatically changing slowly, 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 stop, maps the Hamiltonian back to itself up to a gauge transformation. And this means that the system can have changed its energy only by repopulating the original states. But that is only possible at edges, because only at the edges are there states at the Fermi energy. So the current carried is 1 over c times the change in energy, which is the number of electrons, the number of states which are transferred from one side of the sample to the other, times the chemical potential difference between the two sides, divided by a flux quantum, which is the answer. So, in this view of accurate quantization, the proof, if you will, that localization physics will not change the quantum of Hall conductance, even though the number of states is changing, as is their occupation, is that the experiment measures the charge of the electron. The quantum of Hall conductance is quantized because the electric charge of the electron is quantized. And the quanta can be viewed in this context as the same. Now, that's historical perspective. You can imagine my surprise, great joy actually, when I got this preprint from Horst and Dan announcing their discovery of the fractional quantum Hall effect. So what you see here are this experiment is just the same as I showed you. We're sending a current along the axis, measuring voltages. The voltage drop in the direction of current flow is shown here. The Hall voltage between that pad and that one is shown here. And down at the left, you see Klitzing's effect. And then up here, where there should have been nothing, you see a new feature developing and a dip in the parallel conductance corresponding to it. It's failing to get deeper as you lower the temperature. It says, no, we checked all that. We checked for nonlinearities. It looks very good. You'll see it hasn't gotten to 0 yet in this experiment. It's on its way, obviously, but hasn't gotten there. So I made a guess, okay, based on my knowledge of these guys and also the way the experiment was going, namely that localization physics was also happening here and that it would be complete when the temperature was lowered. Also, if you look at this line, just with your eye, center it with your eye, you'll see it's already 1% accurate. And that was already too much. There should have been no reason for it to be 1% accurate, even that accurate. So there was every reason to believe that the effect was the same as Klitzing's effect, except at the wrong fraction. The filling factor, rather than being an integer, was 1/3. Now, Horst, the experiments got better. Here is a later one. So the guess was right. Here's a later one showing the 1/3 plateau. Very well developed. It's very, very deep minimum here. And you can notice also subsidiary fractions here at 2/5 and 3/7. Now, as the samples improved, fractions of all sorts began popping out. And Horst likes to say, well, what a neat thing it was that good old Bob invented this equation to explain it all, but the truth is I didn't. And even worse than that, I was really lucky. In fact, the world was lucky that the samples were so lousy when the original experiment was done, because had we known about all these other fractions, we would have been very confused. So anyway, it was a lucky break for everybody that this 1/3 just happened to be the biggest one, and therefore the most obvious. Now, how accurate is this experiment? Well, as I told you, you can eyeball it. The original ones were percent. The modern error bar is about a part in 10 to the 5th. And most of us see the only impediment to getting it better being the temperatures to which you can cool the 2D electron gas. That means we have the same problem with the accuracy of this fractional Hall plateau that we had with the integer ones, that it's already too accurate to be explained by modeling. There really must be a principle involved to make it so accurate. Unfortunately, the localization principle that we knew won't work here, because any problem that can be adiabatically continued to non-interacting electrons must have integer plateaus. That's the essence of the thought experiment that I showed you. That means that this quantum state, whatever it is not continuable to non-interacting electrons, but is rather some sort of many-body effect that involves the Coulomb interactions. Now, by far the easiest theory to make right now is that this effect is the same as this one, except that the thing being localized is not an electron, but a piece of an electron, an elementary excitation of the problem that has fractional charge. Now please note that I'm talking in the sense of the principle of adiabatic continuability. So I'm imagining a limit of the problem where the objects, if you will, elementary excitations, become non-interacting and free. In that case, we have localization physics just as before, but not localization of electrons, but instead localizations of the elementary excitations of this state, whatever it is. Now, I can't emphasize too strongly that the reason to believe this is the experiments, not the theory that I'm about to show you. The experiments tell you that there must be fractionally charged excitations in the problem because there is no other way out of accounting for the accuracy. The accuracy is the key thing. There has to be a principle. The principle you have available is localization. Localization of things deformable to electrons, free electrons, won't work as a matter of principle. So by far the easiest thing left is just you have a new vacuum where the excitations are fractional. Now, all that was left now was to invent a prototype that everybody could understand. Now you folks, probably many of you are too young to remember that in those days there was already a big literature on fractionally charged excitations that goes way, way back to papers on solitons by Jakiv and Rebbe, done here actually, and also work done by Bob Schrieffer at Santa Barbara in systems which have what we call discrete broken symmetries in them. So the idea that there should be vacua with fractionally charged excitations is not originally to me. It's due to people who went before me, chiefly particle physics and Bob Schrieffer. So one already knew that the idea was not nuts. The only thing left was to figure out what it might be. Now, I should tell you, when I knew about the soliton work, and so I made a theory of this effect based on an analogy with fractional quantization in solitons, and I sent it into phys-rev letters, and I like to say, thank God the referee rejected it. I know later that this referee was Steve Kivelson, and Steve pointed out, well, that your discrete symmetry breaking that you've made in your theory is really continuous symmetry breaking. It's like the stripe idea. And that means it's got a pin, and therefore it wouldn't conduct electricity, and so the whole idea is nonsense. So I got this referee report, and I said, well, unfortunately he's right, so I need to go think about it some more. So I thought, well, this thing, experiments are telling us it has a great big energy gap. So when things have energy gaps, you can get to first base in modeling them just by brute force. So I thought, okay, let's try to solve the problem by computer, starting with 1 electron. That I can do. Then let's do 2. I did 2. That turns out to be easy. You can do that on paper. What does that mean? Nothing. It means somebody, hello, right? Then 3, then 4. So the model Hamiltonian one can study is just a few electrons that are repelling each other coulombically, and for balance, let's put a little pressure in here to keep them in. In these old calculations, there are 2 energy scales. There's a so-called cyclotron frequency and a Coulomb energy, which is E squared over the length associated with that harmonic oscillator energy. And the limit we usually prefer as theorists is this one, where the cyclotron energy is much larger than the Coulomb energy, even though in real samples we're not always deeply in that limit. But it doesn't matter because of the adiabatic continuability. This is the right limit to be in. So I studied, looked at these guys, and solved them, and got the wave functions out, and I'll show them here. There they are. These wave functions I'm showing you are completely meaningless. I just like to show them. Then I found, well, sure enough, the little cluster is kind of doing what the experiments do. As you increase the pressure going this way, the mean square area changes and jumps, and the angular momentum also changes and jumps, as though it's contracting. It has preferred densities, and it's contracting discretely. So I thought, that's good. Then I said, well, okay, well, that's what's happening. Then maybe something like this thing down here is the ground state. So I knew this wave function is exact when the number of particles is 2. It's pretty close when the number of particles was 3, 4, 5, and 6. So I spent several weeks trying to prove that it was the exact ground state of the relevant Hamiltonian. Relevant Hamiltonian in this case is non-interacting electrons plus a little bit of Coulomb balance potential in the background, jellium basically, plus pairwise Coulomb forces. And it wouldn't work, and it wouldn't work, and it wouldn't work. And finally I said, well, it's not going to work. Okay, this doesn't work. It's a great idea, but it failed. So I went in the physics library at Livermore and began reading books on helium. So I thought, well, helium's like this, and I could learn from helium. And the very first book I pulled down was Gene Feinberg's book on many-body theory. And I opened it at random, and there, on the very page I had opened, was this wave function. It turns out that this functional form for many-body problems is used very commonly. It's called a Jastrow form, and it's variational. So I thought, oh my God, that's it. The wave function isn't exact. Wave functions many-body physics never are. So the thing is variational. So I quickly went to find out how good it was. Now, just so you folks know what's written here, a Z1 through Zn are the locations of the electrons in the plane, expressed as complex numbers. So this is a pairwise difference raised to a power. The power has to be an odd integer. And then because of the background magnetic field, it has to be canceled by an exponential, 1 for each electron. And the length scale in this experiment is the magnetic length, which has been set to 1. So as luck would have it, I was in a laboratory that specializes in plasma physics, and the nature of the calculations that I had to do were all the same as those done in dense plasmas. So I went to my plasma buddies, Forrest Rogers and Hugh DeWitt, and asked them how to calculate, and they showed me, and then one by one, things began to fall into place. So we square the wave function to get the probability to find the electrons at various positions. integrate out all but one of those coordinates, and we get the density, the charge density of the state. And sure enough, it was exactly uniform out to the boundary, and the density is exactly what we want. It's 1/nth of the ideal density of a filled Landau level. The first non-trivial value of m, by the way, is 3, which is the 1/3 effect. Also, one can integrate out all but 2 of the coordinates and get what's called the pair correlation function. And that's important for well, here's what it looks like. So what this is this is the density of the fluid given that as a function of distance, given that one of the particles is at the origin. So in electron gas lingo, this is the exchange correlation hole of the gas. What you see is that the electrons avoid each other. So if one electron is at the origin, then the other electrons avoid it, although in the m equals 3 state, which is the interesting one, they pile up a little bit at the near neighbor position. So once you have this function, then you can weight it by 1 over r to get the energy. Now, just to show you, there was at the time a straw man, which was Hide and Phil Platzman, I guess, their Hartree-Fock calculations for the Wigner crystal. And so it was possible to weight this pair distribution function by 1 over r and find that the wave function I made was a little better energetically because it keeps the particles a little bit farther apart than the crystal. So here is total energy as a function of filling factor. Here is the straw man Wigner crystal energy. Down at the bottom is the 1/3 state I constructed. 1/5 looks like it's better, and then 1/7 it's a little hard to tell. Okay. So on the basis of this calculation, I predicted that there should be one more of these fractions, namely 1 at 1/5. And when I finished this calculation, I phoned up Horst. I said, Horst, I think there's another fraction. He said, really, what? I said, 1/5. He said, well, it's close. What had happened in the meantime was that these guys had discovered the famous 2/5 state, which unfortunately I did not predict. And then they began to find all sorts of fractions that I didn't predict and didn't find 1/5. And that was as my father used to say, cheap thrills. And they didn't find it, and they didn't find it, and they didn't find it. And then finally, I believe it was Emilio Mendez found it in this experiment. Now, there are better, wait. There are better experiments. I just wanted to show this one to demonstrate the lengths to which theorists will go to declare victory of their theories. Okay? In fact, modern samples have a nice plateau here, although it is one of the weakest ones ever found. Well, let's just get that right off. Okay. Now, what about the fractionally charged excitations? Turns out you get those for free. Once you have a uniform state with an energy gap, then you can imagine a little thought experiment where you poke the sample with an infinitely thin solenoid, adiabatically wind a little flux, a magnetic flux through it, a whole flux quantum, and then once you've done that, again, the Hamiltonian has returned to itself just like it is in the loop problem, and so you can remove the solenoid by gauge transformation, and this process gives an excitation of charge plus or minus 1/3, depending on which way you wind. The basic reason for this is the following, that the winding process does something complicated near the solenoid you don't understand, but far away from the solenoid, the effect is very simple. It's exactly the same as in the integral quantum Hall effect. It just takes the state and moves it over by one orbital. And so the net charge transported through an imaginary Gauss's law box here is the average charge per orbital of the ground state, which in this case was 1/3. One thing led to another, and I cooked up these variational wave functions for the positive and negative quasiparticle. Z0 here is not a variable, it's a place locating the center of this particle. So it's a quantum number. These wave functions came out of the blue. They were just the simplest approximations I could think of that would look something like this thought experiment. Later, Duncan Haldane and Ed Rezai did numerical calculations on the problem and found out that these wave functions were vastly better than they had any right to be. So these are actually pretty good representations of the problem with Coulomb interactions. What these particles look like is this. This is what they look like. This is a plot of charge density versus how far you are from the center of the particle. And we want to look at the solid line here. That's the positively charged one. What you see is near the center of it, there's a place where the charge density of the fluid is missing. And when you add up the deficit, it's exactly 1/3. The quasi-whole wave function is this dashed line, and it's the opposite. The charge density of the vacuum near the center is in excess, and when you add it up, the amount in excess is exactly 1/3. Now, with these wave functions, then, it's possible to compute the Coulomb repulsion of the piled-up charge with itself, and then compare it with measurements of the energy to make such a particle. These measurements which do that, or which we believe do that, are shown here. This is a plot of the parallel resistance versus 1/temperature done in the dead center in a plateau. And what you see is, as you cool it off, which goes to the right, there's a region where you get Arrhenius behavior, transitioning to what we call variable range Hoppening behavior at lower temperatures. Both of these behaviors have lore associated with them. This is a strong localization effect, and this is what you expect to get very generally with thermal activation of particles from a chemical potential up to a mobility edge. The mobility edge distance ought to be something like the gap of the state. So one can take this slope and convert it into an energy gap and compare it with what one gets in theory. Now, when this was first done, it didn't work so well. This is a plot of measured activation gap versus field strength. Here are the measurements down here, and the theory is this dashed line. However, shortly thereafter, Alan MacDonald realized that the model is too crude. There's a big effect missing, which is the thickness of the 2D electron gas in the vertical direction. So it has a finite thickness, and when one takes that into account, a good hefty fraction of the deficit goes away. And the rest of it, at least I just described to, well, being good enough for government work, because this relation of the mobility edge energy to the actual gap is a little vague in the first place. Being comparable in size is enough, especially when the trend is right. Notice, everybody please, that the energy scale we're talking about here is quite low compared with the natural Coulomb energy scale. So the fact that it has this trend with magnetic field and is also the right size is very significant. So we got that right. Now, the last thing I want to talk about is gauge forces. It somehow came to pass in the development of composite fermions, which are perfectly right, by the way, that the following amazing property of these quasiparticles got overlooked, I think. This has always struck me as one of the most important and the most amazing properties of these objects, and that is that they exert forces on each other that are velocity dependent. This was first figured out by Frank Wilczek and Dan Arovis and Bob Schrieffer, who took the trouble of adiabatically exchanging two of these quasiparticles, theoretically, and discovering that the so-called Berry phase for adiabatic exchange was a fraction. In this experiment, you get an odd multiple of pi when the particles are fermions, an even multiple of pi when they're bosons. This particular multiple was neither one. In between, it's a fraction, and it's a fraction associated with the charge of the particle. What that means physically is that when one of these particles moves in the presence of another, it feels a fictitious vector potential, as though there were a solenoid being carried by the stationary particle, carrying a fraction of the elementary flux quantum, where the fraction is associated with the charge. Now, the really neat thing about fractional statistics was that it was figured out about the same time, and I think actually before, empirically by Bert Halpern through graphs like this. Bert figured out that if the fractional statistics were present, then the quasiparticles themselves could recondense into new fractions. And those fractions would come out to be the observed ones, namely 2/5, 3/7, and so forth, if they had these solenoidal forces on them. So this is a total energy calculation pulled out of one of Bert's papers, and we don't have to worry about the details of it, just notice that it has some interesting features at the fractions at which the so-called hierarchical states occur. Now, my interpretation of this state of affairs has really not changed over the many years, namely that the observation of these fractions other than 1/3 amounts to experimental proof that the gauge forces are there. The gauge forces actually are emergent in this problem. Even though there is more than one way to describe it, the physics of emergent velocity-dependent forces is definitely present in the problem and has physical measurable effects. Okay. Now we go back to the premise now. After all is said and done, what have we learned? Well, like most wonderful things in physics, this particular discovery has implications. Okay? It was not expected. It was completely out of the blue. It has very many interesting aspects, particularly those relevant to small devices in solid-state physics, semiconductor engineering, and so forth. But the thing that matters to me mostly as a theorist is the bigger issue of where the strange rules of the vacuum might come from. And always when you have an experiment, God is on your side. In this case, we do have experiments. We have accurate quantization, which is telling us what? That there are indeed fractionally charged objects in the world that are collective in nature. They carry a quantum of charge that is as exact as the electric charge itself, of the electron itself. And they also have very powerful forces between them, which are not postulated in the underlying equations of motion, but simply emerge. A new vacuum and a new kind, fundamentally new kind of quantum emergence. At least for me, and I hope for you too, eventually, this has been an exceedingly thought-provoking thing, and I believe and hope that it will have major implications for physics of all kinds as we move into the next century and millennium. All right, that's all I have to say. Thank you very much for...
talk. We have time, I think, for a couple of questions. Yes, Patrick.
Yeah. Maybe I lied. Sorry, Patrick, we have a parity problem. Wait. Yeah, here we go. Here we go.
The picture that had the loop.
Right. Excellent question. Let me answer that now so that your students will understand this henceforth. Okay, let me answer this now, Patrick, because this, you all should know that Patrick and I have been arguing about this for 10 years. Okay? Well, yeah, right. My hair is grayer than yours, so I can't admit it. The answer, of course, is that when the loop is small, so that there's a Bohm-Aharonov effect, then the Hall conductance is not quantized. Yep. Yes, but that's a no-brainer, Patrick. Wait. Patrick, this is already known. If you have something that's one or two atoms, one or two magnetic lengths big, there isn't any quantization of anything. Ah, interesting. Now, interesting question. Now, nobody knows. Patrick, okay, I'm sorry. I'm preaching here, look. I don't know how it depends on L. What I know is that when the sample is too small, you can see it, it's there, and therefore the quantization argument is false. So one has to be in the thermodynamic limit for the argument to work, and that's because localization is a thermodynamic concept. Now, you're absolutely right that the disappearance of the Bohm-Aharonov effect in the thermodynamic limit is part of the argument, okay? I guess the best answer I can give you is it's like localization. See, I can't prove that either, okay? But the scaling hypothesis leads me to, plus experimental facts, okay, lead me to believe very strongly in localization. And so by the same token, I'd say that if we have a loop that's a centimeter in size, I assure you, you will never see the Bohm-Aharonov effect. I assure you. Oh! Yes, now Ray, I made Ray a bet that an effect that he saw was due to, what did I say? I said it was time-dependent delays in transport. And Ray made me this bet in public at a semiconductor meeting. And then, well, should I tell the rest of the story, Ray? Well, I don't know. I think probably we ought to pay each other $50 and then go have a beer. What actually happened was the experiment was, the voltage in the experiment was driven a little too hard, and the effect was an artifact of the measurement. So who's culpable there? Yeah, true, it's a different artifact. But I say, if you demand the $100 under those circumstances, you are a scoundrel. I think we should buy each other a beer and call it a day, Ray.
Right.
Right, yeah, right.
I think at that note, let's thank Bob for a beautiful talk.